All right. Good morning, everyone. So let's get started for our today class. So let me just briefly remind you of the schedule. Okay. So today in the morning we are having a lecture, and then in the afternoon we are going to have mini project presentations. All right. So each of you have a maximum of 15 minutes for both your demonstrations and presentations. Right? So that's the maximum of that. So we probably have total 9 people, but some of them are missing today. So we probably finish the presentations maybe an hour or so. And then so I think since we have a lot of things to cover in the morning, so probably we will have one lab in the mornings and then another lab after the presentations. All right, so that's the schedule for today. And then for tomorrow, we probably will have presentation first for the rest of the class. And then after that, we will have another lecture that will cover object detections. Basically, it's deep learning for object detections. All right. So uh, last week, we have covered some sort of a basic machine learning algorithm, right? For example, k-nearest neighbors. And then we also have covered the linear classifier. All right, so we have learned some sort of basic algorithms of that we can interpret some of the functions as a linear classifier. So then we perform in the lab. We already have our hands on how we can train the linear classifier to classify some sort of data or some sort of images. All right. So today we are and then from last week, we left with some of the questions that we have been answered. So then we are going to cover it in today's lecture. All right. So in today's lecture, we are going to learn about the optimizations, for example, gradient descent and back propagation. So I'll walk you through what are those and then how they works, and also how they're important, right? And then we'll take our step, dive deeper into probably one of the most important concept in deep learning, that is neural networks, followed by the convolutional neural network, which basically one of the most important concept in deep learning for computer visions, right? So that's what we are going to basically cover today, all right? So from previous lecture, right? We already learned some sort of let's say that we have some data set in which it consists of a pair of image and labels. And then we have defined some score functions, right? We have defined some score functions, how, and then we also have defined some of the loss function, that how can we measure the performance of the models. For example, we have defined softmax, multi-class SVM. So, and also we touch a little bit on regularizations. We have already learned what is the responsibility of regularizations when we use in training our linear classifier. But there's one question that we haven't answered yet. That is, how do we find the best W, which is a weight of the models, right? It's either linear classifier or other models. So we need some sort of matrix, right? So that's what we call weight or learnable parameters. So after we train some for the model for some time, and then we have a score function, so we calculate a loss functions. But the question is, how can we determine that what is a particular set of W that we that we should pick for our final model? So that's what we are going to learn today. Okay. Before I dive into how can we perform the optimizations, so let me just briefly walk you through the the training loop of any machine learning model. Most of them are, I would say, 90% of the machine learning model would have to go through all these training loop, right? So just for your reference, maybe some of you haven't have experience on training any machine learning models, and then probably in the lab we already learned something about the training loop. How can we set a learning rate? So those probably might confuse you a little bit. What are these steps have to do with training the machine learning model? So in this slide, I will give you the overview of how we are going to train the machine learning models. All right. Most of the time, we will do something like this. All right. So the step one, we have to prepare our data set, right? So the first thing they have to do is after having our data set, all right, we have to split them into three data sets, right? In previous lecture, we already learned the different strategies. How can we split our data set? But for the best practice, we mainly split our dataset into three sub dataset, that is training, validating, and testing. All right. So after we split our dataset, we'll perform what we call data augmentations and normalizations. All right. Data augmentation for computer vision would be performing some sort of rotation, translation, subtracting, something like that. So those are the data augmentations. And normalization would be, for example, you normalize a pixel value. All right. So you probably normalize it, or you probably standardize it. All right. So that's the way you have to perform this normalization. So your entire data set will have the same means and standard deviation. So there are fall under the same distribution. So that to say, all right. So that's the very first step, and kind of important for us to before we dive into training our models. So all right. And for this, probably when you do any data science projects or any machine learning projects, so you will spend, I would say, 60 to 70% of your time working on this thing, right? All right. So spreading, trying to explore your data, how to perform data augmentations. Probably you need to process your image before you feed into the model. So in the step one, prepare your data set would consume probably 60 to 70% of the time of your project. All right. So it's very important, but it's some sort of labor intensive, but it's very important. All right. So it will help you to have some easy to train the model if you have a good data set. All right. So most of the time, I will spend my time on this very first step one. All right. So I'm not just like jumping into training models without looking at the data, without cleaning the data, without performing any data augmentation, normalization, something like that. So I'll spend my time mostly on this step. All right. Prepare my data set very well before I jump into designing the model, because designing a model is very easy. Training a model is very easy if you have a good data set. All right. So the keyword here, a good data set. All right. You need to have a good data set. All right. So to make your life easier later on. But in some probably in some cases you cannot you can you don't have control over your data set, right? So probably in that case, you have to deal with optimizations of the models, designing some sort of complex models. If you cannot think of any other algorithm, or think of any other data pre-processing algorithm, so that way you can switch your focus to the model size, right? So, and then after that, after you already prepare your data, the second thing would be your model weights. So, right. So at the very beginnings of the training loop, the model weight will be just randomly initialized. All right. Just random, pick any random number. So that's what the model does. Okay. And then in the training loop, so we first we already split our data set, right? So we select the training set first, and then we will loop through the training sample and then feed it into a models. So here's the keywords, or the terminologies that I want you to know. So first, epoch. So what is epoch, batch size, and iterations or steps? So these are really important terminology. You will hear that often when you're working with machine learning models. All right. So let's say that, for example, we have in our training data set. Let's say that we have 100 images. All right. So we have 100 images, and then we are saying that we want to feed in these many images. So when we are training the model, we are not feeding the mod we are not feeding images one by one, right? So that will take forever to train the models. So what we are going to do is we are taking a batch of an image as an input. All right. So let's say that we want to make a batch of 5 images at a time. So we feed in 5 images simultaneously into our models. So that's what we call batch size. Okay, batch size. And then what is epoch? What is epoch? Epoch is that um, you have 100 images, you have a batch size of 5. All right. So which means that you need to feed the models 20 times, right? You need to feed the model 20 times so that the model can see all the 100 images. All right. So that the epoch is the number of loop that the entire data set was seen, which means that let's say that you want the models to see this entire data for 10 times. You train the model 10 loops. So that's the epoch, the number of epoch. So the number of epoch is the number of loop that the model see the entire data set. All right. And the number of iterations is the number of step that the model take to see the entire data set once. All right. So that's the iteration. For example, we have 100 images and then the batch size of 5. So which means that it takes the models 20 times or 20 steps to see 100 images in one loop. All right. Once the model see 100 images in our data set, we call that one epoch. All right. It takes for batch size of 5 images, it will take 20 iterations or 20 steps to complete one epoch. All right. So that's what this means. Okay. I hope that's clear. If not, let me know. All right. So we keep feeding in the models. So and then for each batch, the models make a predictions, right? The model make a predictions for the labels of each images. So after the models, so that's what we call forward paths, right? We feed in the input, the models compute something, and then it gives us the prediction. So that's what we call forward paths. And then we will calculate a loss or a cost function to measure the performance of the model, the predictions of the models, right? So we can use, for example, for the regression problems, we can probably use, for example, mean square errors. And for the classification problems, we can probably use the cross entropy loss, like we learned from last lecture. So the question is, what is regression problems? and what is the classification problems? Anyone knows the difference between the two? When we are talking about regressions and classifications, what are the difference? Because the thing is that it is important for you to know whether what 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 kind of problem that you are working on. You are working on either regression problems or you are working on classification problems. Why it is important? Because you need to pick the right loss functions. All right, you need to pick the right loss functions. If you pick the wrong loss functions, so your model will never be converged. All right, will never perform well. So what is regression problem? What is classification problem?
Regression problem, which means that you try to predict the numbers. I mean, continuous number, let's say temperature, pressure, price. So mean square errors, root mean square error, or mean absolute errors, it kind of the common loss function.
Okay.
So
Yeah. Yeah.
for classification, you try to predict the class, which mean the category numbers. Let's say 1, 2, 3. That's going to be corresponding to class number 1. Let's say the cancer, non-cancer, or my cancer. That's the kind of the class you want to predict.
Yeah.
So the class function normally is a cross entropy or like log loss function, etc. That's the things.
Yeah, that's correct. Yeah, that's perfectly explanations of regressions and classifications. Or if I can summarize this into two terms. So regression problems is a task of predicting continuous value, right? You are predicting continuous value. And the classification problem is the task of predicting a discrete value, right? So the class of it, if the class of each image is nothing but just a discrete value. All right, it's either 1, 2, 3, 4, 5, so that's discrete. So for the regression problem, like for example, you want to predict the price of the stock market, you want to predict the price of the house, you want to predict the price of the car, something like that. So these are the continuous value that you want to predict. So that's the regressions problems. All right. So after we calculate the loss function, and then we will use these loss functions to update the parameters of our models, right? So because at the beginning, step 2, the model is just randomly initialize the value. So each weight value just randomly initialized. So after we see the performance of the model, which means that we know that we need to adjust the parameters or the weights of the models. So we will use this cost value to tell us how much we need to adjust the parameters, right? So after we calculate the loss, we will use the loss value to guide us to perform the parameters update. So that's what we call the optimization. So that's basically what we are going to pay our attention to for today. That is the optimization. So the optimization here, or in other term, we call a backward parse, in which what we are going to do is to perform the back propagation. So we are going to learn about the back propagation today as well. And we are going to see the optimization algorithms such as stochastic gradient descent. So how it worked, and then how it works, why it worked, something like that, right? So that's what we are going to learn today. And also we are going to talk about the learning rate as well. So after the parameters gets updated, we will do this loop, right? We will do this loop until the number of step which means that, for example, we have 100 images, and then we feed in 5 images at a time. So this loop will loop over 20 times. So that's complete one epoch. All right. So which means that we are looping until the model sees every image in our dataset, in our training dataset, right? And then after that, we will test our models between that. We are validating the model using a validating dataset once, right? we train a loop so the model see everything, and then we test it once, and then we test it once, we loop it back again, train it again, validating, and then loop it back, validating, something like that. So that's the complete the epoch. So the number of epoch, it's entirely up to us how long we want to train, and then how many epoch we want to train. All right. So it's just trial and errors to see whether when is the loss function will get saturated. Maybe that's the number of epochs that we want to stop training the models. All right. So that's these are the training loop of mainly the machine learning model will go through this training loop, right? So any questions about training loops?
No, clear, very clear.
All right. So then, if there's no questions, so let's come back for the questions that we left discussing from previous lecture. So the optimizations, the goal of optimization is that we want to find a functions which is a set of weights to achieve the lowest loss, right? So that's the objective of optimizations. So as we can see from these equations, right? So we have a loss function in which we have a set of functions over here that is our models, right? It is a function f of x and w, right? So, and then we compute the loss value of this function with respect to the ground truth, and then we sum them all up, and then we find the average of that models. And then what we want to find is that we want to find the set of W that give us the lowest loss, right? So this is it. What this equation tells us is that the W star here is the optimal set of parameters of the weight that the models can give us so that we achieve the lowest loss, right? So that's what it means here. So that's what so argmin, which means that we are searching for the lowest loss functions, all right? So if you look at the functions, the model as a function f of f, the function f, right? So what we want to find is that we want to find a function f, the star here, which means f, the optimal f, all right? Where that f, if we are feed our training data in, and then the models predict something, and then we calculate the loss, and then we expect to find a function that give us the lowest loss. Right? So that's what the objective of optimizations we wanted to do. All right, so that's bring us to the first optimizations algorithm, that is gradient descent. All right, so gradient descent, if you consider it in terms of one-dimensionals, it is in one-dimensional, the derivative of a function give us a slope. All right, derivative of the function give us a slope. So, but in multiple dimensions, for example, 2, 3 dimensions, the gradients, right? The gradients is the vectors along each dimension, which means that for each dimensions we calculate the slope. So gradients, in other sense, it means slope, right? Gradient means slope. All right, so the slope in any directions, right, is a dot product of the directions with the gradients, and the directions of the steepest descent is the negative of the gradients. So what does that mean? So what does that mean? Let's consider this function, right? All right, let's consider these functions. So just keep in mind that our objective is that we want to find a set of weight or parameters that minimize or that achieve the lowest loss. So that's the objective of optimizations, right? So let's say that our model have two parameters, right? Our models have two parameters, which means that we are working on two-dimensional space, okay? So if we are plotting a space of W0 and W1s against a loss functions. So this is a J of W0 and 1 here is the loss function. So we're gonna get this sort of landscape. All right. So as I mentioned in the training loop, at the very first or at the very beginnings of the training loop, we are going to randomly pick any values of the W's or the weight of the models. Let's say here it's W0 and W1. So that's the weight of the models. So we first randomly pick like any initial value for the models. All right. So let's say that we unfortunately badly random pick at this location, the value of W1 and W2 at these locations. And then if after we compute, so sometime if you're lucky enough, right? Sometime if you're lucky enough, you probably end up picking the point somewhere around here, initial value somewhere around here. So your models probably will converge very fast to the global minimums. All right. So, but unfortunately, in this case, I have a bad luck. Initially, random it's somewhere around here. So, if the values of the W1s, all right. So, what's happening here is that let's see. So this is a landscape of weight, right? This is the space of our weight. So this one is a plotting of loss functions with respect to our weight model, right? So that's it is. So for example, we have a weight of, for example, W1 0.7 and W0 0.7 and W1 probably let's say 0.6. So this is where our model is, and then we pass in some input, we pass in some image, all right, and then the model make a predictions of the label. So we want to calculate the loss value over here, all right, and then unfortunately at this weight value or parameters, we'll get this loss value over here, all right. So we get this loss value over here. So what we want to do is that what we want to do next is how can we adjust, right? So like in the training loop, we want to adjust these two parameters, that is the parameters of the model. We want to adjust the value of these two so that we get a lowest loss value, which is probably at this location. That's we want to go from here to here. All right, we want to go from here to here. So we want to find the values of W0s and W1 that give us this point. So that's what we want to do. All right, so next. So what we are going to do next after we get the loss function, right? So next we are computing the gradients. All right. So the gradient is nothing but telling you the slope or the directions, right? Like I mentioned, if you are taking a derivative of loss value with respect to the weight or the parameters of the model, you are going to get a directions or the slope, all right, or the slope. So basically, the slope at any point, it will be positive. It will be positive. It will be pointing upward. That's the gradients. All right. So this is the gradient you get. All right. So what we are going to do next is that we are going to take a small step in the opposite directions of the gradients. All right. After computing the gradients, we know that our gradient is pointing this in these directions. Right. But what we want to do next is that since we want to minimize the loss value, so that we need to take the opposite directions, right? We need to opposite directions so that That's where we are going down here. We are going down here, right? So we are going down here. We're gonna get the size. We're gonna get the value of the new value of W1 and W2. All right. After we step down, we can pick the value of W0s and W1 over here as the model's parameters. And then we feed the data in again. It's computer loss. All right, it's computer loss again. So we will get a loss value at these locations. We compute the gradients. We take another step down. All right. So we will perform this. So we will perform this. We will repeat this step until we converge to the global minimum, so that we're gonna get the loss function that is minimum loss function with this set of parameters. That is, for example, at this point, probably the value of W0, for example, would probably be 0.4, and the W1 would probably be around 0.7, something like that. So that's the optimal values for the model parameters that give us the lowest loss value. All right, so we keep repeating so that we're going down the hill until we reach the global minima. All right, so if we are going to look at it in terms of pseudocode, all right, so we can say that we first initialize the weight randomly with any distribution. So basically we are using normal distributions with zero means and these standard deviations. And all right, so we are going to loop until converge. All right, during this loop, we are going to compute the gradients. All right, we are going to compute the gradients d of j w, which is the loss value with respect to the d of w. All right, we compute the gradients, and then we are using this gradient to tell us whether we should increase or decrease the weight of the parameters. All right, so we update the weight, that is w minus some small step. All right, so this is a small step, or we call learning rate. So we'll talk about learning rate later. So this gradient, right? This gradient tell us whether we should increase or decrease the weight. All right, so and then we take a step from there, and then we subtract the value from the previous value of parameters. All right, so if the gradient is going down, if the gradient is going, if the gradients tell us that we need to go down, which means that this term is going to subtract the value from this value. So we keep updating this. We keep doing this, right? So we have to update the weights repeatedly until we reach the global minimum. All right, so that's the final weight of our models. All right. Is that clear about the gradient descent, how it works?
Yeah, very clear.
All right, so the questions left is how much, right? The question left is how can we update this weight? How much we should update each weight? All right, so that's bring us to the back propagations. All right, so that's being up to the back propagation. Let's say that we have a very simple functions or a simple models z over here. So all right, x is our input. We pass this x. All right, we pass this x. We multiply x with w1 and then pass it into the hidden layers. And then we perform another multiplications, right, with z with w2, and then we got our final predictions, y hat over here, which is the predicted value for this x. All right. So what we have to do is we compute the loss, right? Whether how good is this predictions y hat. All right. So that's where we compute the loss, j of w. So we want to know, so if the loss value at this if the loss value, for example, 0.9, or the loss value is pretty high, how can we adjust the weight W1 and W2 over here? So what we have to do is first, right? We want to first calculate the gradients, or we want to calculate the gradients of the Wj with respect to the W2, right? So if we split this out, if we split this equation out, we can see that it can have a chain rule. For example, here, the change, right? The change of this W of this loss function J of W is, if we make any change with y hat, it will also have a change with respect to the loss value, which means that if the prediction is good, the loss value will go down. All right, so which means that these two parameters, they are dependent on each others. So which means we have to calculate the gradients to get whether how much W2 affect the final loss value, which means that we have to go back to see whether how much is this change in the predictions affect the loss value. So we can split these equations out. So to achieve the change of loss with respect to W2, we can perform the change, that is the derivative of J divided by derivative dy hat over here, multiply with dy hat divided with dW2. All right. So we compare the change. If we change this W2, how much it is going to change, how much it is going to affect the loss value. And we apply a chain rule. All right. So we apply a chain rule. So because we want, so the objective is that we want to update the parameters of W1 and W2. But the thing is that how much we should change the value of W1 and W2. All right. So we are performing the back propagation because we want to know whether how much W1 and W2 each individually, each of them affect the final loss value. That's why we are performing back propagations and using a chain rule. All right. So if we want to know for the W1 how much it affect the final loss here, so we are using this one. But if we want to know W1, we need to back propagate to y hat z until we got this we got to the W1. So we apply the chain rule so that if we want to know whether how much W1 affect the final loss, we have to go through d of j divided by d of y hat, multiply d of y hat divided by d of z, this is z, and then we go back again one step, d of z divided by the W1 over here. All right, so that's how we find how much the W1 affect the final output. All right, so that's the back propagations. All right, so we repeat this for every weight in the network using so that we know how much this particular set of weight affect the final loss value, so that we can know how much we need to adjust them. All right, so that's the objective. So after we know how much each weight in the models affect the final loss value, but next we want to know how much I need to adjust, or if we look back to this landscape, which means that how long should I step? All right, how long should I step down the hill? All right, how large should I step down the hill so that I can minimize the loss? All right, so the learning rate will control the speed of convergence the speed of you going down the hill to find the minimum loss. All right. So that's bring us to what we call the running rate. All right. So the running rate is control how much you step down the hill or how much you change each parameters, either W1 or W2. All right. You know that W1, how much is affect the final output. W2, how much is affect the final output. But learning rate will tell us how much we will change this, how much we will change this W1 and W2. Because we don't know the ratio, or we don't know the rate that how much we should update this to value. All right, so we use learning rate to tell us that. All right. So how can we set the learning rate, right? So if you set a learning rate, very small learning rate, which means that you take only small step down the hill. All right. So it will the model will slowly converge, or sometimes it didn't converge at all. Because why? Oops. So by setting the small learning rate, why it is slowly, or sometimes it is going to get stuck at a fault local minima. For example, here is our initial case, right? So we are going to take a small step over here, because we set a very small learning rate, right? We are taking small step. Probably when it reach here, it cannot, because we are taking small step, it cannot goes up the hill and then go down the hill again, because the step is very small. So probably the models understand that maybe this point is the global minima. So it's getting stuck here, or it's getting stuck here. So you don't see any improvement in terms of performance. All right. So that's the downside of setting small learning rate. But if you're setting a large learning rate, so for some reason you might never converge, or you even diverge, or we call overshoot. Why is that? For example, this is the initial case, right? And then you take a very large learning rate. So you're probably taking the first step over here, and then the next you update the weight and then compute the loss function again. You probably overshoot somewhere around here. And then when you get here, you might probably overshoot over here, and then you keep overshooting back and forth, never get to this point because of the large learning rate. You take a very large step, right? When you walk with a very large step, you probably never get down to the global optimal. It will overshoot. All right. So that is the large learning rate when you set the large learning rate. So if you set a pretty optimal learning rate, you will eventually getting a smooth converge. Oops. You will eventually get a smooth convert and then get down to the global minima. All right. So the question is so probably you have a very high, low, and good learning rate. So we probably initially we don't know which one is good, which one is bad, right? So the question is, how do we pick this? How do we pick the learning rate, right? So in reality, all of this could be a good learning rate. It depends on your problems, right? It depends on your problems. It depends on your model's architectures. All right. It depends on your data. So probably this all of this very setting very high learning rate, setting very low, or setting some good learning rate. It could be all good learning rate. It depends on the problems at hand. All right. So which means that we have to try and errors with which ones are the optimal learning rate for our case, for our problems. All right. So there are many ways that we can deal with setting learning rate. All right. So instead of just setting a fixed learning rate, we probably can using the adaptive learning rate. So we can probably start with a very large learning rate and then reducing the values of learning rates as the training loop goes on. All right. So for example, we probably have using a learning rate decay. So we take a step, right? For example, training for 30 epochs, we reduce a learning rate by some amount, and then training another like 60 epoch, we are reducing the learning rate again. So this is one way. So we call learning rate decay, or we can use a cosine function. All right, we can use a cosine function to calculate how much we can reduce our learning rate as the training loop goes on. All right, so these are the techniques that we can use to perform the adaptive learning rate. Okay, or there are many algorithms, or there are many ways that we can perform the learning rate decay. For example, step, cosine, or linear, or even inverse square root. So these are the things, or these are the way that we can perform the adaptive learning rate settings during the training period. All right, and for the gradient descent, there are many algorithms, or we call the optimizer. All right, the optimizer. So each and different optimizer can act differently to calculate the gradients, and then how to adjust the parameters. Right. So these are at least just a short list of the optimizer that we can use when we are training the machine learning models. For example, stochastic gradient descent, Adams, ADA delta, ADA grad, or IMS prop, root mean square property. So we are not going to discuss the optimizer in this lecture. So if you're interested in a deep diver into a more detail for optimizing the gradients, or for the optimizer, you can visit this website. I think it is very good explanations about optimizer in this website. So basically, one of some of the short lists of popular optimizer would be stochastic gradient descent, Adams, and then I probably sometimes see people using IMS prop, something like that. But mostly they're using Adams. Okay, so yeah, this is the optimizer. Okay, so we have already learned some how we can perform the gradient descent algorithm. How can we adjust those, right? So let's look at some of the gradient descent optimizer, right? So let's look at the stochastic gradient descent, all right? So if we look at the algorithm in terms of a pseudocode, so we are going through the same pseudocode, or same algorithm. So first, initialize the weight randomly. Right, and then we keep looping until it is converged. So inside that loop, we are computing the gradients and then updating the weight. But the difference here is that if you look closely here, the computations, or the gradients computings, if we compute this for every sample, or for every image in our data set, let's say that we have a very large data set. Like if we use ImageNet, we probably would have millions of training images. So if we compute a gradient for each and every image in the entire data set, all right, so it will be very computationally intensive, because you have to calculate everything. You perform back propagation for every images. That will be very computationally intensive. Okay. So the workaround would be, for example, we pick just one image. All right, pick just one image to represent the entire data set. All right, to represent the entire data set, and then compute the gradient with respect to that image only, and then use the gradients from that image to tell us how much to adjust the weight, to update the weight. All right. So this will be very noisy. All right. That will be very noisy to compute. Just pick a single data set and then compute the gradients and then adjust the weight. All right. So that's not possible. I mean, it's possible in terms of implementations, but you will get a very noisy adjusting parameters for each and every single image. All right. So for this one, you compute the gradients for all the image, all right, for all the image with respect to for all image. So that's why it is very computational intensive. But for this one, you just compute the gradient for every single image and then update it. All right, update the parameters with respect to a single image. But for this one, you compute the gradients with respect to all the image and then update the weight once. All right, so that's the difference. So this one require a very heavy computations, but this one, if you choose to go this way, compute gradient with one image and then use that gradient update the weight. Doing this for every image, that will be very, very noisy. All right, and one of the best way to do is we call a mini batch. All right, a mini batch is that you pick batch of B data point. For example, if we have 100 images, we probably pick a batch size of 5. All right, and then you compute a gradient based on this 5 image, just 5 image, and then you use that to update the weight of the model, and then you keep repeating this for all for all the image in the data set. All right, so this will help us speed up the compute and give us a better estimates of the true gradients. So which means that we are just subsample images from the data set and then compute the gradients based on that, and then use that gradients to help us update the parameters of the models, right? So this is what we call a stochastic gradient descent using a mini batch. Okay. So the mini batch, while training, it help us help us get a more accurate estimations of the gradients, smooth convergence, and then allow us for a larger learning rate. So which means that if we use a larger learning rate, so we could probably convert to the global minimum faster. All right, and so that it leads us to a fast training as well, because we can parallelize computations and then achieve a speed of GPU. All right, so that's the stochastic gradient descent with mini batch. Right. So to summarize, we already learned how a linear model works for image classification models. We also learn about how we can express our preference over different choice of weight by using a loss functions. Also, a loss function we use to quantify the performance of the models, how good or how bad it is. And then we just learn about how we can use the stochastic gradient descent to minimize the loss so that we can achieve the set of weight that give us the lowest loss. All right, so that is the set of weight that we want to achieve for our model, so that we can use this set of weight for deployment for productions later. All right, so these are the concept in this training loop of machine learning models. All right, so any questions?
So normally we use mini batch, but the batch size is vary and need to test.
Yeah, so we normally use a mini batch in training. So the batch size is depends. So it depends on what first depends on your data set, whether you have how large your data set you have, right? So if you have a very large data set and then use a very small batch size, so it's like you have a millions images and then you're using just 8 images at a time. So you will get a very, very noisy gradient. So because you have to go through all that millions images many times, compute many gradients, update your weight many times. So if you choose a very large batch size, so that probably consumes most of your GPU memory, because when we put, let's say, like 10,000 or 1,000 images into a GPU memories and then compute, let that calculate make the predictions, calculate the gradients, update the value. So that's very computational intensive. All right. So the values of batch size depends on how large is your data set. So you should avoid a very noisy update weight, which means that if you have a very large data set, you should increase the batch size. But when you increase the batch size, you have to mine your own GPU memory. All right. So you cannot just increase to infinity, but your GPU, let's say, for example, if you are using RTX 3070, right? NVIDIA 3070. So it has, if I remember correctly, it have like 16 gig of RAM. So you have to manage those 16 gig of RAM. So if you have many GPU, you can parallelize them. So which means that you can distribute the task. So you can increase the number of the batch size as well. So yeah, so the size of the batch, it depends on these two parameters mainly, these two factors mainly, the size of your data set, and then your the size of computationals you have.
Yeah, clear. Thank you.
Mhm. Any other questions regarding this? All right. So if not, let's move on. So if you look back at a linear classifier, right? So we probably see that if you look at the linear classifier from geometric viewpoint, we can clearly see that if we have a data set that have this sort of distributions, the linear classifier won't work, right? Because we cannot find linear equations to separate these two class of objects or these two class of entities, right? So we clearly cannot find any linear equation to separate between the two. Or if you look at the from the visual viewpoint, we can see that the one template per class will not work. So the question is, how can we solve these problems? But we want to use linear classifiers. So how can we solve this sort of problems? Let's say that we want to use linear classifiers. All right. So the solutions is that we can do something called features transform. All right, features transform. So let's say that this is the original space of our data. So the equations that we can use to in this original space of our data, the equation that we can use to separate between the two classes probably be a circular the equations of the circle, right? But the linear model cannot do that. So, but we want to use a linear models to do it. So what we have to do is that we have to perform a feature transform. So in this case, we are transforming this original space into a polar space, right? So for example, we are transform that using these equations. So what we end up is in a feature space. So this is what we call a feature space with respect to theta and r. So this is what we got when we performed a features transform. So then after that, if we using a linear classifier in this feature space, we can see that it can clearly separate between the two classes. So which means that if we want to use a linear classifier, in some problem, we probably need to perform a features transform so that the linear equation works in that particular space. All right, it can clearly separate between the two classes. All right, so yeah. So we can see that we can so go further that for the image classifier long in the past before we have the CNN convolutional neural network. So what people does is that perform this features transform. For example, the image here we can perform the color histograms. All right, we convert or we count the number of each color in this image and then use this, we're going to end up with this histogram, right? And then we use this histogram to perform a linear classification as an input to the linear classifications. So instead of just use a raw pixels or use this image, feed it in the linear classifier. So we first convert it into a color histograms, which means that we are performing a feature transform from features into dimensions, right? The pixel. So we transform this into a histogram, which is one dimensions. So that's the features transform. And then we insert or input these features into the linear classifier. So we hope that by performing this features transform, the linear classifier will work better. We work better in terms of classifying the categories of the image. All right. Or another techniques that we can use for image features would be a histograms of oriented gradients. So I hope you remember this concept, right? So for every pixel, we can in our class of corner detection and edge detections, right? We can calculate a gradient of each and every pixels. All right, so I hope you remember that. So a histogram of oriented gradient, it's just like what we perform in a feature descriptor, right? So in a feature descriptor, which means that we want to find signatures of any particular blob. So we are just counting the gradients of each pixel under that blob. But instead of just looking at this at any blob in the image, we are looking at the entire image. We're looking at the entire image and then perform a histograms of the gradients of each and every pixels in the image. All right, so we're going to get a histogram of gradients and then use this as an input into a model, a linear models. So, and then hope that this kind of feature transform will help the linear classifier to separate between different classes of images. All right. So basically, for the linear classifier to work well, we probably need to help it some sort of feature extractions, or we call features engineering. All right. Instead of just passing a raw image, but we perform a features transform or extract some feature first, and then pass that features into a linear classifier. So this kind of feature extractions help linear classifier to have a higher performance or higher accuracy. So that's what we did in the past, long before the deep learning eras. All right, so that's what we call machine learnings. So we still have to help it. All right, we still have to help it to extract some features from input or extract some features from the images first. All right, so this is manually done. This is manually done by human. All right, this is manually done by human. And then we feed this the extracted features into the models, and then it learn from there to come up with some sort of boundary, so come up with some sort of linear equation so that it can perform a classification between the different classes, right? But when we are talking about deep learning, we are talking about deep learning, all right? We are going to eliminate humans from the loop, right? From the loop. So which means that instead of us as a human thinking a way how to extract a features, what should be a good features that will help the models get a good performance. So we as a human don't want to do this. We humans are lazy, all right? So we as a human, we are lazy. So we don't want to do that task. Okay. So that we migrate or we mitigate this task to the models. We hand over these features extraction to the models, right? So in deep learnings, the models, right? So this is what we call end-to-end learning, all right? End-to-end learning, which means that this end is a raw data and the other end is the output, is a result. All right, so that's what we call from end to end. So you just have a raw data, feed it in, you just wait for the final predictions. It's end-to-end learning. All right, so it perform feature extractions, it performs some sort of calculation and give you a prediction final output. But for the image above, it's not end-to-end. It's not end-to-end because from going from raw data, you still have to perform some feature extractions. And then you feed in this feature extraction into the model, and then it will learn these patterns, and then it will give you a prediction. So it's not end-to-end because there's a human in the loop, human in the middle, extracting information from raw data to get some feature before feeding into that. But for deep learning, it does everything itself. Okay, extracting features, extracting patterns, combine some information, and then give you the output. All right. So that's the difference. Okay. So that's bring us into the concept of neural network. Okay. So I think before we going further, let's take a 10 minutes break and then come back. We will discuss more about a neural network and then going into the convolutional neural network later on. All right, so let's come back at 10:26, 10:27. All right. If you have any questions, just maybe you can ask for now. If you don't have questions, can take a break. Back. Right, so let's continue with the next topics, that is neural networks. All right, so we are going to dive into a neural network. So let's first compare the biological and artificial neurons. So if you look at the biological neurons, so we can see that it consists of a nucleus, that is the process unit of the neurons, and then it has a dendrite that receive the impulse or the electrical signals from other neurons, right, other cell. And then the nucleus process the informations from those electrical signal, or we call impulse. All right, and then it will send out the impulse or the information that it's already processed through what is called axons. All right, so that's where it sends out the electrical signal to another cell or another neuron in our brain. So that's how the biological neuron works. All right, and the artificial neuron is trying to imitate it's not exactly the same. So we just used to compare them, just not side by side, but it's not working exactly the same, but just simulate the behaviors. All right. So artificial neuron try to imitate that. So we have the cell body, right? So we have the cell body. So this cell body receive the information. Receive the information. For example, the image pixel values x zeros, and then each cell have a drain drive, right? A drain drive that is performing the multiplications between the weight and the signal that is coming in. So the cell bodies will sum everything up, right? So the drain drive here perform the multiplications between the weight and the input that is coming. So the cell bodies perform summations or additions of all the information that came in, and then using using the activation function to decide whether how much information it will pass through or activate this information, pass the impulse or pass the information through other neurons in the networks. So the way it works is kind of same, but the internal operations kind of different when we compare with the biological neurons. So that's the analogies that we can compare between the two, right? So we basically the neurons, the smallest units of the neurons, so we call the perceptrons, or another way we can call neuron is the perceptron, right? So you probably might hear these terms somewhere else. That's what the perceptrons, all right? So in the forward propagations, we have this sort of input, right? X1, X2 to Xm. And then we have a weight or the parameters of the models, W zeros to Wm. So W zero is probably we call a bias term, sorry. And then it has some sort of summations, and then the activation is nothing but adding linearities into the neurons or into the information. So we will discuss about this later on. So, but for now, just for your information to know that the perceptron, it has the inputs coming in, performing multiplications with the weight, and then perform a summations, apply some nonlinearities, and then it gives us the output, right? So if you look at it in terms of a linear functions, we can see that the output y hat is equal to a linear combinations of the inputs. So this term at the back, summations from I equal to 1 to m's, the input xi multiplied with wi from I from 1 to m, right? So this is a linear combinations of the inputs and the weight parameters. And in many cases, we just add a bias to just shipping the information around. And then all these sum up together, pass it into a nonlinear functions, which is we call the activation function G over here, that will eventually give us the output of y hat. All right, so that's how the perceptron works. All right, so if we look at them in terms of matrix multiplication, so we can simplify these terms into the X transport multiplied with W, right? So the X would be a column vectors. So then we multiply with this matrix, all right, with this, or it can be vector as well, vector multiplications. So we're gonna get this a simplified terms of these functions. All right. So for the activation functions, right? So the activation function, it just the task is to add a nonlinearity, right? So in terms of linear models, right? Linear models, we just the model is just only to estimate or to approximate a linear boundary for our data space, right? For our space of input space. So it only approximate the linear equation that separate the informations from each other, separate the informations or separate the data from different classes to each other. So in terms of neural networks, we are not only wanted to perform the linear classification, but we wanted to approximate any functions, all right, in our data so that it can be non-linearity. So we are using this activation function to add the non-linearity into the models, all right? So if we take this non-linearity out, if we take this non-linearity activation function out, the perceptron is nothing but it's just a linear models, all right? It's just a linear models. If you look at this equation, it's just simply a linear models. That's it. So we add this activation function so that the models or the perceptron or the neuron can handle the non-linearity characteristics of the informations or of the input data. All right. So the example of the activation function would be, for example, these sigmoid functions. So if the values like goes to infinity, it will be zeros. If the values of z, so this is the z over here, sigma, like goes positive, it's got more than zero, it goes up and then eventually saturated to 1. So the values of sigmoid, it will press the values of input. I mean, it will compress the value, or it will shift the value of the output from the neuron to be ranging from 0 and 1. That's it. All right, to be ranging from 0 and 1. All right. So which means that, so if the summations, if the multiplications and summations of this neuron given some negative value, it will be ranging from 0 to 0.5. And then if it is giving a negative value, it will be ranging from 0.5 to 1. But everything will be ranging from 0 to 1. All right, so that's the sigmoid functions. So there are multiple activation functions that we can use with the models. For example, ReLU, TANH, Ligi-ReLU, something like that. So these different functions can influence different behavior of the models. All right, for example, for the ReLU, right? The model is just consider it's either or it's only consider the positive value from these operations. All right. For if anything that get negative, it would be 0. All right. So that's a ReLU. So if so like I mentioned that the activation function is to introduce a nonlinearity into a network, right? For example, if we have this sort of data, right, in the original space of this data set. So if we are going to use a linear models, it won't work, right? It won't work because there's no linear equation that can separate between the two classes, right? So if we introduce or if we add the activation functions into the models, so the models can handle this sort of very complex function, so that it can estimate or it can approximate this function and then can classify different classes of the data. All right, so that's the roles of activation functions in the network. Okay. So the property of the activation function would be it need to be the differentiable, right? Because we need to perform a back propagations. So in order for us to be able to perform a back propagations, any elements in the chain rule need to be differentiable. All right, and it has to have the very small computational expense. All right, it has to be inexpensive. For example, ReLU, you did nothing but to check whether the value is positive or negative. It is negative, you just give it 0. If it is positive, you just keep it as it is. Right, so the computational is very inexpensive for that case. And also the activation function, it needs to be it is most of the activation function are monotonic in nature. So monotonic means it's either increasing or decreasing, so which it can simplify the optimization process. All right, so yeah. So what we learned so far is just one single neuron, it's just individual neurons. So to make a neurons or to make a models like have some sort of perform better or get a very good performance, we need to connect them together, right? Like in our brains, we have like over 80,000 80 billions cells, 84 billion cells in our 84 billion neurons in our brains. All right, so all the neurons are connected together and then perform each own task. So likewise, if we connect the neuron together, all right, so that's what we call a neuron networks. All right, a neuron network is nothing but a collection of neurons. We connect them together layer by layers. All right, so multiple layers networks we'll call multiple layer perceptron, all right, or MLP, or sometimes you will hear some people call fully connected layers or fully connected networks, or sometimes you will hear people call this sort of architecture or network is dense layers, all right. So the very first network is that you connect every neuron here in the layer in the blue, you connected every neuron or every perceptron with every input. All right, so that's what it called fully connected. All right, you connected with the input and you also connected to the output. All right, everything connected together. But this neuron and this neuron are not connected together. Okay, it's just connected to every input. Each neuron in hidden layer here just connected to every input, and it is also connected to every output. All right. So we can if we wanted to do a more complex task, we just stack them together. All right, stack the blue layers together and then connect them together. So this is what we call a fully connected layers. Okay. So inside each of these neuron, it's just performing this, all right, just performing this operations. All right. In one neuron, it just perform a summations and additions. So this is one neuron. Okay, this is one neuron. So for each and every of these neurons, it just perform that additions and summations. Okay. So for example, if you look at our input image here, it has 32 by 32 pixel by 3 channels. All right. So we stretch this out. So we're gonna have total of 3,072 numbers. All right. We have 7,032 numbers. And then we can connect each and every numbers pixel value to every neurons, right? To every neurons in this layers. All right. So after performing summations, we will come up with this output from maybe like categories of the image from cat, dog, what else? Cats, dogs, elephant, something like that. So that's how the neural networks work. It's just a combination of this. All right. We just connect them together. Right. So so why neural network is a powerful functions approximations, right? If we go back to the linear classifier, right? So let's say that we have this data set, and then this is a distributions of the data set, right? So we can clearly see that we cannot use a linear models to perform a classification on this data set. So we perform some a feature transform, right? So still in this feature space, we still cannot do a linearly separable between the data set, right? But if we use a neural network, so then we can introduce these activation functions or nonlinearity, so that this mapping function from these distributions, it can go like that. It can transform to this, so that we can clearly see that after we introduce some nonlinearity ReLU, for example, so we can use a linear equation to separate the data in the feature space. So that's where the activation functions or nonlinearity function comes in. Okay, so that helps the neural networks can approximate any functions, not just a linear function. It can approximate polynomial function. It can approximate a very complex function. For example, something like this. It can approximate a psi functions. It can approximate a polar function as well. Okay, so that's why a neural network it's kind of the powerful function approximations. Okay. So setting the number of layers here. So setting the number of layers in the middle. So that's what we call a hidden layer here. So setting a number of layers here and their size. So the more hidden layers, the more capacity, right? So the models or the network will be able to compute a very complex structure. It will be able to compute a very complex functions approximations, more complex function decision boundaries it can do if you increase the number of layers and their size. So the size means how many neurons in one layers. So it's like you increase the number of neurons in your brain. So you will get better and better, right? You will get more genius, something like that. Okay, so as we can see from here, 3 hidden layer unit might not be able to handle this data set very well. So if we increase to 6 hidden units, it will perform better. But if you increase up to, like, for example, 20 hidden unit, it will try to approximate and then try to classify all the sample in your data set perfectly, right? But if you remember in last class, we are saying that we don't want the models, or we don't want a function to be very complex, right? We want a simple models that can perform well, or that can generalize to the data that it never see before. So trying to increase the number of units, or try to increase the number of hidden layer might probably be good in the training time, but it will not good in a testing time, right? Because it's just trying to optimize, or trying to approximate the train, or trying to fit into the training set only, but it will not generalize. So we want the model to be the most simple one, but still good for both training and testing data set. So that's why in the previous lecture, I mentioned that to tell the models that we want the final parameters to be very simple, but still have a good performance, so we can use regularization terms in our loss function. So it will help the model trying to generalize to the data set, or trying to generalize to the problem itself. Okay. So any questions about neural network?
No, very clear. Thank you.
Okay. So now we know about neural networks. So we are going to go another step, which is a convolutional neural network. So I hope you remember the term convolutions from our very first lecture, right? So we perform those convolutions using the filter image, trying to blur the image, trying to filter the noise out. Those are the convolutions. So now we are going to apply the convolutions to the neural network. So that's why it's named convolution neural network. So CNN for short. So if you go back again to our the problems of linear classifier, or even multi-layer perceptron. So as I mentioned that in linear classifier, and MLP, we need to stretch the image out to be as a vector, right? Instead of 32 by 32 by 3, so we stretch it out to be a 3072 numbers as a vectors, right? So by stretching the pixel into a columns, so what is the problem? So the problem is that we lose the spatial structures in the image. All right. So the pixel next to each others, they might have some correlations, or they might have some related features to each other. But when you stretch it out, so that means you destroy the spatial data, spatial informations from your data. All right. And also by stretching this out, and then you connect every value pixel to every neuron. So that means there are many parameters, right? So if you look at this, connections, there are many parameters, right? Each line corresponds to a set of weight, right? So if you stretch it out and then you connect everything to the next neuron in the next layer, so you will have lots of parameters, lots of weights, right? So that's the problem with linear classifier and MLP. All right. So the solution is to define a new operator that can operate on a spatial data, right? Which means that you don't want to stretch the image out into columns. You just want to keep it as it is to retain the spatial informations within the image, right? So we need some sort of that operator. All right. So if you look at the components of fully connected layers, or multi-layer perceptron, or dense layer, this term we use interchangeably. Okay, so we already have seen a fully connected layers and activation functions, so we already know this too. So for the convolutional networks, they are using that as well, but they have the additional components, or they have additional operator, that is convolution layers, pooling layers, and normalizations. All right, these are the additional components that CNN have over the fully connected layers. So we are going to discuss about convolution layers and pooling layers only, but we are not going to cover normalizations. Just leave it, okay? So let's first look at the convolution layers first. So in fully connected layer, right? Like I said, you stretch it out, you're gonna get a vectors of 1 by 3072. You multiply that with a weight, and then you end up with a number, right? That represent a class of that particular input. All right. So you stretch it out, But as we know that there's a problem losing spatial informations, and there are many parameters. So in convolution layers, we want to preserve the spatial structures or spatial information within the image. All right, so that's what we want to do. So we'll keep it as it is. So let's say that we have the image of 32 by 32, right? That's the width and height of the image. And 3, that is a channel, red, green, and blue. All right. So we want to perform a convolution so that we define a filters or kernels, right? So it just similar to what we did in features extractions that we learned about the gradient filter, the smooth filter, something like that. It's very similar, okay? But in image, in that lecture, what we learned is that our filter, it has a fixed value, right? It has a fixed value. It's already defined. The value inside each elements of the filter is already defined. For example, we have a Sobel filter, right? It already have the value inside each element, like 0, 1, 1, something like that, all right? But for the convolution, each element in these filters is randomly initialized. So these elements will become what we call a weight or a parameters of the models, right? So we will design a filter to match the size, not to match the size, to match the depth of the channels of the image. All right. So for example, here we have. All right. For example, here we have defined these filters to be 5 width and 5 height, and then channel here is 3. So it's 3 this matching with this depth, right? So then after that, after we get this one, so each elements of this, so for example, we have 5 by 5, right? We have 5 by 5. 5. All right. So like I mentioned, in traditional image processing, we have a fixed value for each elements in the filters. But for convolutions, this value of each element will be randomly initialized, and then it is learnable or adjustable by using a back propagations. All right. So which means that we can change the value of these elements in the filters. Right. So we have 5 by 5. So what we are going to do, we are going to convolve these filters. We are going to convolve this filter with this image. All right, we are going to convolve, which means sliding through this until we cover the entire image. All right. So by sliding, you are performing convolutions, right? You are performing convolution, which means that you're just mapping this. I'll explain it. I have slides, so it will give you a visual understanding of the convolution. So we convolve that, so which means we're sliding over the image, especially, right? So yeah. So here's how we do. Since we have 3 channels, right? We have 3 channels. So and then we have the filters also 3 channels. So each of the filter in 3 channels, it's just sliding over, right? It's just sliding over. So when it's sliding, it perform element-wise multiplications and then sum all them up from each channels and then add them together from all the channels into output one result. All right. So for example, red, green, and blue here, it's just sliding over the image, right? Sliding over image, and then you perform a multiplication each time you sliding, sum them up, you get one element over here, and then you slide that, and then after finish everything, you sum everything up from all the channels, and then you end up with a single result over here. So that's how the convolution works, right?
Excuse me, is this we call this a canal?
Yeah. So this small filters over here, the thing that we slide over here, this thing over here. So
Yes.
there are 3 names. It can be used interchangeably. It's called kernels, or
Yes.
it can be called filters.
Yes.
So there are 2 names, not 3. Kernel and filters.
Yes.
Yeah, you
And
can use.
so the problem of the neural network here that when we input an image and the neural network flatten it into a dimensional vector, so the neural network they cannot they lost all of the proximity or shape or edge and texture. So with the CNN, with the convolution, we can filter and can define the kernel that then we can get the connection between the pixel of the image. Is that right?
Yeah, right. You're right. You're totally right. So by performing this, by doing this, right, you lose some special information from
Yes.
the pixel over here, right? So if you stretch it out, you look, for example, these 2 pixels, they might have some correlations. There might be some information that connect to each other. But if you
Yes.
stretch them out, you lose
Yes.
that information, right? So, but by using convolutions, we preserve that special informations. So
Yes.
then when we convolve this filter or kernels with this one, what the kernel does is here is it just learning the patterns under that, learning the pattern under that filters. It's just trying to extract what we call a local features, all right? The local features under that kernels only. All right, so it's trying to learn using the special informations under that kernels, and then trying to extract the information for that. So that's what we call a local features. Okay.
So that means in real life, if we want to classify the disease cancer or not, we using the neural network. And if we want to classify the X-ray, we use CNN. Is that right? In the real life.
In the real life, it depends on the input. It depends on your input.
Yes, it depends on the input. If we want to classify the disease, cancer or not cancer, we're using the neural network. And if we want to classify the X-ray, the picture of X-ray, we're using the convolution neural network.
Partially correct. So go back to your first problem. You want to predict either cancer or not.
Oh, right? Classify.
Yeah, classify whether cancer or not. Yes. It depends on what kind of input you use.
Yes.
So, for example, to classify whether patient got cancer or not, if you are using the informations, for example, using their weight, their height, the data from the lab, right?
Yes.
So you can use a neural network. You can use a neural network, which is probably multi-layer perceptron.
Yes.
But if you want to detect the cancer from X-ray image, from X-ray image, so multi-layer perceptron cannot be used. It can be used, but it can use as part of the network.
Yes.
Okay. Right. So that's why I'm saying you are partially correct, because it depends on what input data. Yeah. Yes. If you're using image, X-ray image, so you have to use convolutional neural network. Yeah.
Yeah. Thank you, Professor.
All right.
Question. Just to make myself clear. This kernel size is let's say 3x3 or 5x5. The three things, right? If we have RGB, but this is the initial weight.
Initial weight, yeah.
Let's say the 3x3, you random make it, and then this kernel will be this kernel will be the same. Let's say initially this weight, and then you do the back propagation to update these numbers to get the right, I mean, not the most optimization kernels things when we do the back propagation, right?
Yeah, right.
Clear.
So
before we study is let's say Gaussian or median kernels, it's kind of fixed things, and we apply to the input and to get the output.
Yeah, right.
Now it's a learnable kernel. Okay.
Yeah, right. It's changeable. Yeah.
Thank you.
All right. So for example here, right? So you perform your sliding, you convolve over the spatial location, so you will end up with what we call the activation maps. All right. The result of convolving the filters with the image, so we call activation maps, or sometimes you will hear people say feature maps. Okay. So activation map and feature map, it's the same thing. It's a result of convolving filters and the image, right? So that's what we call activation functions. So for example, here we have the result of taking a dot product, all right? It's at the dot product. So dot product is multiplications and additions, okay? So yeah, so it's probably sometime we keep doing this, okay? We keep doing this. Probably we have multiple filters. So we are not using just one filter. We can use many filters, all right? So because one filters can extract one patterns, right? One filters can extract in each layers of the convolutions. You can have multiple filters. All right. For example, in this image, we have 6 filters. We have 6 filters. So what we expect from this 6 filter, we expected to learn to extract different patterns from the image. So if you are using just one filters, it might be able to capture just one pattern. For example, if we go back to the example of the horse, right? For example, the horse probably looking at the to the left and to the right. So if you have just one filters, it might probably be able to detect the horse that facing to the left only, but not to the right. All right. But if we add more filters, we expect that the networks or the models will be able to detect both. Either the horse will be heading left or heading right. So this number of filters, you can add it. You can add it. So you might have a question: how many I should add it? The answer is it try and errors. It depends on the problems. It depends on the size of the image. It depends on the number of sample. All right. By increasing the number of filters to some extent, to some level, it might help you increase the performance. But up to some certain levels, the performance of the models might not increase. All right. It just stop there. All right. So you have to try and errors, but there is a best practice that they use in terms of in practicals. So probably the first layer would be some sort of 512 filters or 1024 filters, something like that. All right. So if in this example, if you have 6 filters and then you convolve each and every of these filter with this input image, so you're going to end up with a stack of activation functions activation maps of size of 6 by 28 by 28. So that's the activation maps that we have after convolving this. And also do not forget that we have to add a vector, bias vector as well. All right. So the question is, why is 28? I will answer that later. Why we have the size of image 32, but we end up with the activation map of size 28, right? So 6 here is clearly match the number of filters that we have, but why 22 become 28? I will answer that later. All right. So in practice, right? We are not feeding image one by one. We are feeding a batch of image, right? We're feeding a batch of image. So in terms of implementations, we have a batch of n images with C channels. So that's if RGB would be 3, right? So the numbers of filter, we have to match that as well. So we are going to have channel in, channel out filters, and then KWKH is the size of the filters. It's either 3 by 3, right? It's either 3 by 3, 5 by 5, 7 by 7, all right? C in here, matchings, it's going to match the channels of the input, all right? How many input for each image. And then C out here, it is going to match the size, which means C out is the number of filters, all right, which it is going to match these dimensions, right? So the output after the convolution will have the same side, the similar side, which is in the batch number of images, because for each image we are performing the convolutions with every filters. So we get this one set of activation maps and then another set of activation maps for each image. If we have n image, so which means that we have this n number of activation maps, stack of activation maps. Okay. So by using convolutions, you can extract, you can stack convolution layer, many layers. Right? You can stack them. So by stacking the convolutions layers, what we wanted to do is that we wanted to extract the first layer might probably extract a low level features. All right, we call low level features. For example, in the very first layer, it might extract a color, it might extract the edges, it might extract, for example, if you are performing a face detections, in the very first layer, it might extract just low level features like edges, lines, corners, something like that. That's the first layer. And the next layers, it will learn as as the number of layers goes up, the patterns or the informations that CNN extracting will be very more abstract. For example, the first layer extract edges, corners, and then the next layers, it will try to combine these edges and then corner together to construct faces, right? To construct eyes, to construct mouth, to construct nose. And then the next layer will combine everything together to get a sense of faces, right? And then after that, it will try to, the next layer, it will try to come up with a this face belong to who, something like that. So that's how it behaves. CNN is trying to extract features from the image. So by using this concept, we are not going to perform feature extractions. All right, as you can see, we don't do any feature extraction. Like I mentioned before, but by using a linear models, we might have to perform a feature transform, that is feature extractions, to convert our image into, for example, into a histogram of color or histogram of gradient first, and then feed that into the model later to help the model to easier being able to classify the image. But by using a CNN, we don't have to do that. We just feed in a raw data, and then it will extract everything itself. It will trying to extract features from the image by itself. So that's why we call it end-to-end learning. All right, this is called end-to-end learning. All right. All right. So if we look at so the question is, what do the convolutional filter learns? So if we are looking back to our linear classifier, so we say that the linear classifier is nothing but it's just one template per class. Okay, so a convolutional layer does exactly something like that, but more intelligently. That is, it is being able to capture the variations per class. It captures variation per class. For example, a variation in terms of the directions of the horse head, the variations in terms of colors of the image. For example, the car would have many colors, so that the CNN can, after performing the convolutions, it can capture these patterns of different colors of the car as well. All right. So that's what it actually, for example, here, if we plot it out, all right, if we visually plot these filters, this is the result of the filters. Okay. So what do we mean by the result of the result of activation maps? So what they are plotting there is this image, this one, to see whether what exactly convolution filter does. Okay, so we are convolving the filter with the image, and then we get this activation maps. All right, if we want to know what is this filter actually extract, or what pattern it's trying to find, so we have to visualize these activation maps, right? So that's what they did here. So they just visualize this activation map of the first hidden layer, so we can clearly see that what are these filters does. So for example, here we can say that one filter is trying to extract some sort of these patterns, and then this filters trying to extract a different sort of colors, something like that. So this is the way how we can see what each filter trying to do, trying to extract, right? So we can visualize if like the results of all the filters in our networks, in our models, all right? But if we are trying to visualize the activation maps in a very high layers, it will be more abstract. So we wouldn't be able to understand what it does. But at the layer 1, 2, 3, so we can somehow understand what it does. All right. So here, for example, from AlexNet, I will explain later. So AlexNet in the first layers here, so they visualize the activation maps here. So they can conclude that the first layers of AlexNet, it's just trying to learn the oriented edges. All right, so that's what it does, or trying to learn the opposing colors. So that's how they know what exactly the model does by visually the activation maps. All right. So now let's talk about the spatial dimensions, right? So after we convolve the image with the filters, right? For example, here we have the input 5 by 5 and filter 3 by 3, right? So the problem is the feature map shrink. So as we can see from 32 to 32 by 32, we end up with the activations mapped of 28 by 28. So the size of the feature map shrink with each layers. Why is that? For example, the resulted dimensions of input 5 by 5 convolved with filter 3 by 3. You're going to end up with the results of 3 by 3, right? You're going from 5 to 3. All right, so we lost something. So in general, we can calculate the size of the activation map by using these equations. Okay, W is the input size minus K, which is the filter size, plus 1. Okay, so if we take this input as an example, we have 5 minus 3 plus 1. So we end up with 3, right? So that's the size of the activation map. So how do we solve this problem? So that's where we have the solution is by padding. So I hope you remember the padding from from the very first lecture, right? We have been we discussed about that already. So in CNN, so we also utilize that concept by add paddings or padding with zeros. Basically, in CNN, we just do padding with zeros. All right. So if you padding with zeros, so we can calculate the size of the activation map by using a similar equations, but we add the term 2p. P is the size of the size of the padding. All right. For example, if we are taking this and then we are padding with let's say 1 or 2, for example, let's say with padding of 1, we're gonna get 5 minus 3, you get 2 plus 1, we get 3. All right. If you're padding 1, if you're padding with 1, just 1 padding around here, so which means that plus 2, we're gonna get 5. So which means by padding, just padding is equal to 1 for the image of size 5 by 5, convolve with filter 3 by 3, padding the input with 1. So you're gonna end up with the same size as the input. You're gonna get activation map with the same size as the input. So we retain the size of the input. All right, we don't want it to shrink over time, but there's a way that we can shrink it later. Right? There's a way that we can shrink it later so that we can reduce the numbers of parameters. All right. Are you clear about the spatial dimensions here?
Yeah, clear.
Okay. So now the next thing that I want to discuss about the CNN, right? So there is a concept of receptive field, all right? There's a concept of receptive field. So for the convolution with kernel size of k, so each element in the activation maps, right? Each element in output depends on the k by k receptive field. All right. So let me use a layman term here. So let's see that let's say that this element, so this each of this grid is the activation maps. Okay, is the activation map. If we look at these elements only, all right, we can say that this element is the result of this area of the output. If the result in filters and this area of the output. So if you imagine that you are at this locations, and what receptive field means that what you see from the image, how large you see from the image. So if you close your eye with this hole, right? This hole, you have one eye, you close your eye with this hole. How much you see in this perspective is your receptive field. That's what we call receptive field, right? It is where you see, right? If you close your eye with just small hole, you might not see the entire image, but you see only part of the image. All right, so that's what we call a receptive field of each element. All right, so the receptive field of each element, it just equal to the size of the kernels or the filters. You understand what I'm saying, right? So for example, the receptive field of these elements is 3 by 3 with respect to the input. But if you are talking about the receptive field of these elements in layer 3 with respect to the output, with respect to the input, it will be entire image.
On.
Okay.
So
you got what I'm saying, right?
this one is the activation map, right? This layer or
Which one?
the layer 1 is the activation map.
Let's say that the layer 1 is input image. Let's
input
take it
image.
as input.
Okay.
Yeah.
And then you put the
and then you have the filter, right? You convolve it.
Yeah, convolve, ReLU, everything, and you
Get
end up
activation
with
map.
activation map 1.
Yeah, then you convolve with that and perform ReLU, you got another activation map 2. So if I ask you what is the receptive field of this with respect to this input image, it will be 3 by 3, right? But if I ask you what is the activation map of this element with respect to the input, it will be 5 by 5, which is the entire image. Why? Because this element is the result of this filter convolve with this area. Convolve with this area, right?
Yes.
Convolve with this area, you get this one. So yeah, this area itself, every element in this area is the resulted from these filters convolve with everything in the image. So you get this area.
Okay.
So that's why we are saying that the receptive field of this element with respect to the input image is 5 by 5. But if we are saying the receptive field of this elements with respect to the activation map 1, so it will be 3 by 3.
Okay.
That means the number of pixels of the original image input that contribute to the decision of output pixel.
Yeah, right. Yeah, you're right. So it just mean that how many pixels this elements see in the input, or how many pixels in the input contributes to the values of these elements.
Good,
Yeah.
good.
Okay.
Okay, so that's the receptive field. All right, so so receptive field for the large image, we need many layers for each output for each of these to see the whole image, right? So we eventually we want these elements, or right, we want each element to see the whole image. But for the very large image, which means that we need many layers for the elements in the very deep layer to see the whole image. So we need many layers to that. All right. So how do we make or shorten the size of the models, right? We don't want to have so many layers, because it will increase the number of parameters. It will increase the training time. It will increase the number of required training samples. So we don't want that. Okay. So we have to do a downsample inside the network itself. Okay. So one way that we can use downsample is to perform a stride, which means that how much you move from, like when you convolve, right, you're sliding. So if stride 1, which means you move 1 pixel, at a time. All right. But if stride 2, this is a stride 2, right? You move 2 pixels at a time. You move 2 pixels to the right, and then move 2 pixels down. All right, so that's this is one way that you can downsample inside the network. So for example, if we have the input of 5 by 5 filter, convolve with filter 3 by 3 and stride 2, all right, you will end up finally with instead of 3 by 3, you end up with 2 by 2. All right, so that's how you reduce the size of activation map, reduce the size of the output. So we can calculate the size of the output by using these equations. So divided the stride from this, and then you added 1. So you're gonna get the size of the output by setting stride equal to 2.
So the stride objective here is just downsampling the input image.
Yeah, it's just downsampling the size of the activation map.
Activation map. Okay.
Yeah, so by reducing the size of activation maps, you are also reducing the number of layers that the elements in the very deep layers can see the whole entire image. So that's one objective. The second objective for downsampling is to reduce the number of parameters. Right? If you like reduce the number of parameters, the number of layers reduce, the parameters also reduce.
So hold. The first thing, we introduce padding to remain the image input. But now we introduce the stride to reduce the image input.
Yeah. So
does it make sense? I think
it depends on so padding added to keep to retain or to keep the size of the image the same, right?
Yes.
All right. And to add the stride, which means we want to downsample. But why do we add? So can we add padding and stride at the same time in the same layers? We can.
Yeah.
We can, right? So, but why we are doing that? Why we are doing that? So, for example, if you are not adding the padding, you will lose some informations. Along these edges.
Yes.
All right. If you are not adding that, so you are adding you add padding for 2 reasons. First reason, to retain the size of the output, right? To retain the size of the activation map to have the same size as input. That's one reason. So the second reason is to not ignore the informations around the edges of the image.
Okay.
So, but for the stride, right? For the stride, we want to downsample or reduce the size of this input so that we can reduce the number of parameters of the models. We can reduce the number of parameters of the models. So we can use both paddings and stride together. So it depends on your objective. If your objective is to both extract the information from the edges and reduce the size at the same time, you use both paddings and stride. If you want your models, you don't care, you don't want to retain the size, you're just adding the stride or not adding the stride, you can the size of the image we keep decreasing. So to some extent, when you design the models at the very first layer, you normally want to keep the size of the image or of the activation map to be the same as the size of the image, just for the sake of extracting informations. Let's say that maybe the first 2 layers, and then after that you will have to perform the downsample, so that you need to reduce the size of the whole, the total models. So by adding stride, or there's another technique we call the downsample. Another technique. There's another technique.
Okay.
Okay.
Thank you.
So we have another technique that we can do that, which is pooling layers. All right. So before we dive into that, just let's talk about let's give you some quick quiz. So if we have the input of this size 3 by 32 by 32, and then we have 10 filters. All right, we want to apply 10 filters of size 5 by 5, and then we want to add paddings of 2 and then stride of 1. What is the output volume size? Without going to the next slide, just trying to stay at this slide.
Okay.
What is output volume size?
W minus K plus 2P, and then what S over S plus 1. Okay.
All right. What is the output size?
W is 32 kernel 5.
So the filter or the kernel is 10.
Mm-hmm.
The shape of the kernel is 5 by 5. Padding 2, side 1. The output is 10, 32, 32.
10, 32, 32?
Yes.
Any other answer? So we have 10, 32, 32, right? One answer, we have 10, 32.
No, it's 16.
We have 10, 32 by 32. So that's
32, 32.
What's that?
No,
32.
cannot.
So what else?
10, 16, 16, I think.
10, 16, 16. Okay. Any others? Any others? Okay. So let's see. Anyone get it right?
Each filter scan on the image input with 3 channel RGB. The padding is 2, stride 1.
All right. So if you're using
the output side is 10, 32, 32.
Yeah, it's 10 to the 32, right? So you have 10 filters. So we obviously at the output, we have 10 over here. We're going to have 10 copy of that, right? And then the size of each activation map, if we are calculating, because we have padding stride 1, we're going to get the same size, right? 32, 32. All right, so that's the output volume. So the output volume is over here, right? Just one image, okay?
You overstride and then you plus one. Oh, sorry. Put
So, and
Oh.
then what is the number of learnable parameters over here? So as I mentioned, the learnable parameters is the weight inside each filters, right? So what is the number of learnable parameters in this case?
So 25 to 250, correct?
How 250?
You got 5 by 5, so 25 parameter per kernel, and then you got 10 of them. So 25 multiply 10, so 250. Correct.
Yeah.
3 channel plus
Yeah.
1.
So this is what you get, right? 3 channels. So this 5 by 5, 3 channels plus 1. So that's one is bias, right? You're gonna get, so for one filter, you're gonna get 76, right? You're gonna get 76 parameters, one filters. So we have 10 filters, right? You're gonna get 76. The next question is, what is the numbers of multiply and added operations? How many multiplications and added operations when we do this convolving or convolutions operator?
Number of multiply.
Yeah, number. So when you perform the convolutions, you're gonna convolve, right? You're gonna convolve each and every elements with each pixels under it. You're going to perform multiplications and then summation, sum all of this. So what is the number of multiply added operations by performing convolutions of 10 filters over this image?
Okay, let me check.
Over a million.
Over millions?
Yes.
Okay.
No. 30.
Right. So what we have is not over million, under millions. All right. So
Okay.
yeah, so you have you have this 10 by 32 by 32, right? Because you have 10 filters. This is your output, right? This is your output size, 10 by 32 by 32. So you get roughly about 10,000 output. So for each output, right? For each output, so you have inner products of 2, 3 by 5 by 5 tensors. So that's 75 elements. So you multiply the two, you got 768,000 numbers of multiply added operations.
Okay.
So why is this important? It just a matter of you can calculate the number of flops. If you're working with GPU, right? There's a term flops, floating point operation. So this is related to that. Okay, this is related to that. Like how many flops when we perform convolutions in one layers with this many filters, something like that. So you calculate the number of flops. For example, if they're talking about the performance of GPU, it can compute 1 billion flops per second. So that's how how much it can perform each times for each convolution layers. All right.
But excuse me. But the filter itself is 5 by 5 and you have 3 channels. So some of the element is 5, 5, 3, and 75. 75, and the first time you do not have to sum. So you need 74 other to put in the total.
No, that the thing is that we are doing
the multiply plus add is 75 plus 74 is 149.
No, that's not the way it's calculated. We are performing inner products.
Inner product. Yes, okay.
Yeah, so it's not like you multiply everything and then you add them up, right? It's not like that. When you perform inner product, this is the thing that you get, the number of
Okay.
the multiplications. All right. So what you calculate is linearly multiplications and additions. So
Yeah,
if you do inner products, so
yeah,
that's how it's being calculated. Yeah.
yeah.
So most of the operations that we are doing in GPU, we are mostly using a matrix operation. So that is either inner products or cross products, something like that. It depends, but basically in deep learning, we are doing an inner product between either matrix to matrix or vectors or matrix, something like that. Okay. All right, so now we have convolution layers, right? And then as I mentioned, within the networks, we have to downsample the size of the activation map or of the input, so that we can reduce the numbers of parameters, as well as we can reduce the number of layers that the elements in the very, really deep layers can see the entire image. All right. So that's bring us to the pooling layers. So it's just another way to downsample, right? So probably you use a kernel size, stride, and pooling function. So these are the hyperparameters that you need to set for the pooling layers, right? For example, we have this 4x4 activation maps, and then we want to perform a max pooling, right, with 2x2 kernels and then stride of 2, right? So we will end up being with the output with 2x2, right? So what we did is just finding a max under this area. So max that will be 6, right? And then we stride 2, so we get this, we come to this, finding max, so we get 8 over here. So we keep doing that. All right. So by doing this, we can downsample the size of the activation maps. So not only that, by introducing the max pooling, our network will have the property of invariance to the small spatial shift. What is that? For example, you have the image of this, right? You have the image of this. And then in your first image, you have a cat or you have a person standing somewhere around here. You can detect a person. But what if this person in another image, you are capturing the same person in another image, and then he or she is sliding, moving to the right to these positions. So to make your models invariant to such a change, all right, to such a shift, so we can introduce the max pooling to help us to invariance to shift by using max pooling. And also a convolutions filter itself, it also invariance to the shift as well. All right. And also we can say that CNN or convolutional neural network, it is invariance to rotations and translations. What it means is that it does not matter the same object of the same class. It does not matter where it is in the image. It does not matter rotations of that object in the image. If it is the same class, it is the same objects, the models will be able to detect it because of the filters and because of the downsampling using these pooling layers. It will help the models invariance through such a change. All right, so these are the two important properties of CNN. Right, so there are many ways we can do pooling. For example, max pooling, average pooling. So yeah, and for the pooling layers, there's no learnable parameters, right? There's no learnable parameters at all. So it helps us not only reducing the size of the input and also the number of layers we need, but it's also reducing the number of learnable parameters that the whole model requires. All right. So, now we have everything we need to construct or to design the CNN models. All right. So we know convolutions, we know activation functions, we know the downsampling or pooling layers. So and also we know a multi-layer perceptrons or a linear or fully connected layer. Now it depends on us how we are going to put this into architecture, into structures, right? So basically, what people does is that they will have a convolutional layers, and then Lilu max pooling, convolutional layer, Lilu max pooling, and then at the very end, they will introduce flattened or linear layers or a multi-layer perceptron. Why is that? So if you remember the space warping, right? So if you have the input of 3 dimensions, that is RGB, right? 3 channels with 32 by 32, so that's 3 dimensions. So if you're using a linear classifier that is fully connected layer or linear models over here, if you simply apply a linear models with 3 layers, right? With 3 dimensions informations, it won't be able to use a linear models or linear equation to separate between different classes, right? As we can see, as we see from the early slides, right? From here. Let me go back here. So from here, right? So let's say that this is the space of the image. And if we firstly, in the very first layers, we introduce a linear classifier only, it won't be able to do that because it cannot find any linear model to separate between different classes. So what we are doing here, what we are doing in by using the convolution first, and then put a linear layers at the back, is that we are doing a features transform, right? We are doing a features transform. So which means that for each and every convolutional layers, we are performing a feature extraction and a feature transform. It is mapping, for example, it is mapping from this many dimension, 1 by 28 by 128. This is the many dimensions of this image set. We are transforming this many dimensions into another space, right? Into another space of these dimensions. I'm not sure how many, 20 by 28 by 28. That's the dimensions of another space. So from space of input, 28 by 28, you transform it to another input. So mapping every pixel value from that. And then you mapping again into another space. So you have 1, 2, right? You have 2 time mapping. And then at the end, you are hoping that by doing these 2 features transform, eventually at the end, at this second layers feature space, you hope that you can use a linear models to separate between the class. That's why we are putting a linear layers over here. All right. So sometimes, in many cases, these 2 feature mapping or 2 layers might not be enough, so that you are adding more convolutional layers, so that, for example, you add 5 convolutional layers, which means that you are mapping data 10 times. You are mapping to 10 different space. And then at the 10th space, you are hoping that this space is enough for the linear models to be able to separate between different classes that you have. All right, that's why we are added the linear layer at the end, because we want the model to be very simple. All right. All right, that's how we construct the convolutional neural network. All right, so for normalizations, we are not talking about that. It's kind of more complex. Okay. So CNN architectures is, if you look at it very briefly, right? In the ImageNet, they have competitions that if anyone can like submit their models and then performance to that. So as we can see that as the number of layers goes up, right? As the number of layers goes up, the accuracy or the errors reducing dramatically, right? So and also they compare this performance with human operator. So for example, the humans in this ImageNet dataset, like 1 million image. So people can make 5.1% errors, but in like from 2015, when ResNet come out, it's outperformed the human, right? It just made 3.6 errors. So which means that the number of layer increased drastically from 8 layer to like 100 something layers, right? So which means that they're mapping multiple times. Okay. So here's the one of the very first architectures that is AlexNet. Okay, that is AlexNet. It consists of, for example, COF1 have a filter 96 filters of 11 by 11s, no padding at all, stride of 4, and then they have a max pooling. So convolve max pooling, convolve max pooling, convolve max pooling, and then finally end up with a linear classifier. All right. So that's the AlexNet. So how can we choose this? How is this configuration is chosen? It is the simple answer is trial and errors. All right. Try to convolve max pooling, linear layers. So it depends on how many. So it's trial and error. You never know when it's gonna works. How many space or how many features transform you need to do. So it has to do a trial and errors. All right. So here's just compare the number of memories, number of parameters, and the M flops that is requires for each and every layers in AlexNet's models. All right, and here's another networks that is VGGNet. All right, so VGGNet come with the concept of using small filters but very deep networks. All right, using small filter, which means that the small number of parameters. So that which means that you can go very deep, but have a similar number of parameters, right? So for example, here, if you compare AlexNet and VGG16 and VGG19, they have roughly the same number of parameters, but VGG can go much more deeper. So the more deeper you go, the more features or the more abstractions you can extract from the image. All right. So the questions why use small filters, right? Like I mentioned, you use a small filters so that the number of layers or the effective receptive field of each one, it increasing larger and larger very quickly. All right. And also then require the number of fewer parameters. All right. And by adding deeper, you add more non-linearity to the data. When you transform from one space to another space, you add more linearity, which means that the models can approximate a more complex functions. Right. Right. So yeah, this is just comparisons in terms of memories and the performance and the numbers of computations that is requires for AlexNet and VGG. Okay. And yeah, for AlexNet, it's also just come up with another some sort of architecture that they're just stacking different numbers and then introducing these sort of residual connections, right? So it is going to add. So the core concept of ResNet it is what problem it is trying to tackle is that as you go deeper and deeper, right? As you go deeper and deeper, the layers at the very deep layers, it will forget some informations that the very first layer have. It will forget because when you pass information along the way, when you pass information to many people, the information will lost along the way, right? If you ever played a game that the first person see everything and then trying to communicate the information to the next person, right? So as many persons standing and then trying to communicate what the first person see, the communication will lost over time. Okay, so the ResNet, that's what ResNet trying to change, is that by adding this skip connection or the ratio connection, so they are adding the informations, the skip connection, so that the deeper layers can still have some clue of what information the very first layer have. So that's it, the main concept. All right, so that's what they're trying to change by adding this skip connections.
Yeah, this one same concept. I mean, the transformer get this concept and they put in the transformer architectures.
Yeah,
The
So,
skip connection, but
yeah,
it's also reduce the what we call vanishing gradient.
vanishing gradients.
Yeah,
Yeah,
this will help a lot.
yeah,
That's
yeah.
the key. It's a breakthrough of this architecture.
Yeah, that's ResNet. It has been used in many. It has been applied to many architecture later on. Yeah.
That's the key things.
Yeah. So yeah, there are many versions of these blocks. Okay. So yeah, probably this is it for CNN. Any questions?
Yeah, let's practice and understand more.
All right. So then in the afternoon, we'll first have a presentations, and then after that, after the break, we will have 2 labs. So you will walk you through the labs. So the lab will consist of, what is it, Yi? I don't remember. We have a deep learnings and a classifier walking through step by step, right? So yeah, so we have 2 labs in the afternoon after the presentations.
Excuse me, Professor.
Yep.
I cannot find where the place I can upload the presentation into Moodle.
Oh, okay. I'll create the submission folders for you guys.
And with I code my code in the Hugging Face. I send you the link.
Okay. Okay. You can also attach the link into the slide as well.
Yes.
Yeah. Okay. Right. If no further questions, I'll see you in the afternoon. Right.
Okay.
Okay. Bye-bye.
You need to skip the lunch.
Everyone is back, so I think we can start maybe in a minute.
Start.
Yeah.
Couple of them absent, I think.
Right. So let's get started. Who will voluntarily start first?
Yeah, that's me.
Yeah. Okay.
Let me set a string.
Don't they press to another?
No, man, I got nothing much. Okay, I got this. You guys see my string?
Yes.
The dinosaur. Okay, but I go there's an agenda. I will make a couple of apps. First of all is gray, which means to convert the image from webcam to the grayscale. Apply the Gaussian blur. with the sigma moving, Kenny H, bright contrast adjustment, and also I try to apply the Panorama app application. Actually, it's not work very well, and yes, I do the AR for my 3D dinosaur. First of all, I go with my first app. So this app have 5 different things. I add the Panorama separately. So build on OpenCV and Python. It's normal, right? Which means that normal image, nothing at all. I convert to grayscale, adjust the brightness, X detection, and using Gaussian blur filtering. The first one is the grayscale. When I do a couple of research and things, the grayscale, they will put the want to convert to grayscale, they apply the weight to each channel of the image about this kind of weight, and it's based on the standard of the ITU something. This standard is the high definition television, and I see that the human eye is the most sensitive to green light. That's why this is the weight highest one. And so in OpenCV, that we just use this kind of function, color BGR to gray. Is the underneath is this, they apply this function to convert to the grayscale. That is the first features. The second one is let me put it here. Is what brightness and contrast adjustment. So basically, it's like in your iPhone or in things, they normally have application to change the brightness, more brighter, less brighter, or put more contrast, see more things, more the picture goes more like pop up in your eyes. So basically, when I do, I mean, before I use Lightroom, it's a very normal, I mean, the application on the PC, on MacBook, they have this kind of thing to adjust the brightness. So I just replicate that kind of function. Most likely on the big picture will be got a plot in a histogram like this. Is the pixel 0 to 2555, and is the how many is count, right? Count base. So in this pixel over here is the highest pixel with a lot of pixel with this kind of numbers. So on the over both, which means all the histogram feature image gonna ship over here. Right both is like in the middle. If the perfect is the normal distribution, and the both with the over the low pixels would be highest one. On the other hand, we have a contrast. So the shape of the histogram going to be shipped would be more a low contrast, and would be narrow down. A normal one, a little bit spread out of the histogram, and spread it all with high contrast. And this function looked by the output, if it the value of the image x and y, I mean y and width and the height, and we apply the brightness over here beta, and also the alpha to increase the contrast. So it's a kind of function here to get the values from the bars adjust and then apply the converse scale by absolute. It's kind of linear function. That's the second features. Third one is Gaussian blur. So most likely the Gaussian blur, we implement a same concept in theory. These kind of things. We have a kernel, more standard version, the larger standard version, the sigma, the more blur, right? So we implement everything. It's very straightforward. And this is the standard we in the theory, 2 pi with the standard variation. So we simplify this 4, make it easier. And we have to, the kernel size should be the odd level. So we just divide it very odd one. And we set a maximum of kernel size and try to see the things. And Kenny X detection. So the Kenny X detection, we have in theory, we learned that we have 5 steps, right? Noise reduction, first step with the Gaussian blur, Gaussian filters, gradient calculation, pay on Sobel. That means that the white the vertical and horizontal gradient, I think. Yes. Maximum suppression, the upper threshold with the lower threshold and the upper threshold, and how hard up the edge is, and the edge tracking to connect the weak and strong edge. That's very straightforward in the theory, and we try to implement with the threshold and the plus sigma as well. And we apply same. We got the noise reduction with the Gaussian noise reduction, put the image more smoothen the image, and apply the Kenny edge function with the threshold from the image that got blurred from before. And panorama. With this panorama, I try to make the real-time things and have the ship with features things, and also he's like the thing in applying the code is kind of for me is one of the most complicated things, and I still got this one working properly, but it still cannot optimize these apps. But first of all is we apply shift to get a feature detector, matching, homography estimation, and inlier outlier with Randstad, I think. Yes, and image wrapping and planning to make the image, but it's not working properly. So I will demo these first apps, and then later on I will continue with the AR application. So I got a string. I will share another string, I think. This one. Okay. So I will go to this app and make a demo. Wait a minute for me. Copy path. By demo app. Sorry. Go here. Copy path. Python app.py. Hey, you got my webcam? Sorry, my background. A lot of toys. Hello. On you can see?
Yes, can
Hello?
see.
Yeah, okay. So it's great. Turn the app, convert the image to gray. I set it normal. I set to bright. I adjust the brightness so the picture more brightest, right? And contrast. See, you put more contrast, and then this pop up. The histogram will change, right? So the image output will be changed. Under expose, very bright, very low, dark, contrast. So we still can see things. That's about the brightness, and I set to normal. What else? Edge. Okay, edge detection. Okay, plus sigma 10. So in theory, we have the if we set the three, the more the edge would be less, right? Because we want to very specific edge only. See, and if the image, our image is more blur, is less edge, right? Let's see. Yes. And if less blur, so it's reserve more edge with the threshold. So if threshold are wide range, we got a lot of edge. Okay, let's set normal. What else? Panorama. Okay, this is the most headache one. Okay, I think this is the feature. I think this shift feature, we have many shift detector over here. And I think if we want to move to the capture the pictures, I just hit space, and it show up how many features in the next picture I'm gonna see, and it's overlapped with the current one with the current image shape. If I move here a little bit out, it's reduced, right? This number, the matching feature between two frames is reduced, and I capture one. I still got messed up here about the blending and thing. I still not figured it out how to read work properly with the panorama. So it's still kind of need to study more and how make it work properly with the panorama.
So so here To get this one, you need to, so how do you capture the image? I mean, you hit some keys to capture the image, or you just let the algorithm run like in real time, and then it will feed it will feed you frame by frame, and then you just make the panorama from there.
I think I use the space bar to capture the next image.
Mm-hmm.
And is the original image, I think, is the below one, and the next one, I think, the below here, and the next one over here.
Mm-hmm.
It's still overlay, I think, some point, and it's extension over here. But the blending, maybe the what we call the final image should be doing properly, because in the lab we have the like static image panorama. Here's the real-time things through the webcam.
Okay.
I think it's not properly doing with this kind of function. How to
And yeah, so how do you implement the overlapping bar? So how do you determine the percentage of good overlaps?
I think the thing we use is the what we call this number. I think the matches between this one. In the theory, we have used the what we call the plot matching, right? The numbers. So if like original one, we have this number live counting. So maybe the next when we move it out, the plot will be changed. This number, the detector feature will be changed because it's a new frame already, I think. And then this number will be reduced. So there's just counting on the original and the next frame image. That's probably that like that.
So which means that it is calculating every pair of the frames from the live camera, right? So because when you because the overlap it just keep changing, right? It just keep changing, which means that every frames in the cameras it used to compare the number of features that are being matched, right?
Yeah. It's a live. I mean, from the manner, it's a live image webcam. So maybe it's need to do with the more real time things rather than the batch with the image we capture by hand, and be blending. Here, I think it's more real time. So it's more, I think, difficult.
Okay.
So that's it. I still not figured it out yet how to do properly.
Okay.
Okay, let's see if my first application. So I will go to the next one is the AR. So with the AR, let me share this one. You got my slide again? Hello. Oh, you got my slide again?
See your VS
No,
Code.
we see your editor.
Sorry. Okay. AR. So you got the string?
Yeah.
Yeah, the AR things is I follow the Dr. Joshak code. So the first one is use the calibrate file, and I use the I print out the trace bar like this. So I do the calibration for my webcam. That's the first step to get the eccentric matrix for my internal webcam to try to calibrate with the image and then try to plot with the 3D things. That's the first step with the code already in doing, and try to apply that one with the chessboard. And I do the next one. I do a couple of research, and then on the internet, and see that they use the Aruco marker which means that I go to this website to make the Aruco marker like this with the 2.5 inches, I think. Yeah. And then which marker is like a QR code, and we help the camera to detect the area to plot the 3D position. That's the concept of the Aruco marker detection. And what next is the I want to download the 3D object in the internet, dinosaur, for example, with object file, and use with the help with some AI, I add more realistic color and things, more easy to capture the image out, and this look like really dinosaur. my son really like it. Okay, is concept here is install everything, and I do the calibration of my camera and hard code to the application like this with the matrix and the coefficient, and the marker size is the Aruco marker. And then yes, this is a step. I think this the demo already in the lab in the class, and I put the calibration files, and I use the AR markers with bring to the camera to see it, and I adjust a little bit more with the size of the 3D objects, because the 3D object from files have a different size, so it's make more realistic. So I can have a function to adjust the slide of the size of the object when we do. So, and then that's I will share my VS Code again. So is CD. So I got Python is my file. Copy file. Oh, you got my marker. You see the dinosaur.
Yeah, that's look good.
Yeah, then with the help I can add the what we call the size, and change the marker. They do a lot of things. So basically that we calibrate and plot the image on this marker, so with the help the camera to detect this area and plot the 3D object on this area. So that is the AR things we in the class.
Okay.
So they know the distance with the 3D. We know the distance from the camera to this marker, 0 point something, right? And I name this marker is number 1, and it's called number 1, and that's it. So that's my AR. Thanks.
So can we put like 2 markers and then it can like project to dinosaur? Have you tried that?
Not yet. Not thinking that.
Okay.
Not.
Okay.
Is it possible? I mean,
Yeah,
2
I don't
marker,
know. Yeah.
and then 2 dinosaur, or
Yeah,
2
2 dino
person.
yeah, 2 dinosaur, 2 markers. Maybe probably we can try that.
Yeah, possibly, yes. I think what possible, it's possible.
Okay, so how do you import the OBJ file into the
Yeah.
AR?
Okay, here's my things. I download this T-Rex object in the internet. But most likely they use the mostly they use in the gaming things, this object. So, and then I put it here. I load this T-Rex here.
Okay.
Load the files in this one and put the scale a lot, because the people create that things for, I mean, game or things, I don't know yet. So the scale have to manually input and make a markers things. I just load it here.
So yeah, so what is a renderer does? What is that functions?
Render function.
Yeah,
This
so
thing. Okay. Initially, the image look to render the 3D object. This is the render function, because when I work initially, it's a cube like in the class. So which means that they use the code Python to draw the cube in 3D things. So which means that you use the code to draw the 3D object. But right now we use the object file with the configuration things. So we use this kind of things to render that out, not like the 3D object, 3D drawing things. So render would be come from the library here. I use some of the library over here, render here. Not library.
So this is a class that you use to render MTL.
Yes. I
Okay.
think this is the one of the input from the
So from
object file.
from which, so you're using ChatGPT, Claude, or something.
Yes.
Okay, okay.
100%.
Which one help generate this code?
Okay, first I need to know the step to do. I mean, the 3 step. I go to the internet. There's one
Okay.
site. At least I know the concept first.
Yeah.
We cannot ask them directly. And then when I know the concept, then I need to bring out these two, right? These two paper. And then I understand, and then I just use the Claude.
Okay.
And then just keep asking, and then but I need to look for the object file, understand the things. But the process is, the dinosaur look very ugly. So I keep asking that because people make the 3D object, they put things like shape, color, things like that, or the more proper one. So I try to get more this thing. So they come with the material or environment things to read the object file properly. So they can come up with this kind of function for me.
Yeah. So did you ask the GenAI whether what is the OBJ file? What does it contain inside OBJ file?
Yes, I did open out
Okay.
the files, because when I Chrome, I try to understand the files, because I want to capture more the inside of the object. Because we should know inside, right? Here is on the vertex. What I think is they draw by hand, and they is the vector things with the side to get the 3D object. So it's render or things could be plotted out in the 3D things. So when I open, I copy these things to the prompt, and they understand that, okay, here's my object in physically the object, and they try to generalize the function more to get the picture properly.
Okay, so so this sort of objects, we will talk about these 3D objects .obj, .pt, or what else? .obj, .pt, .point cloud, something like that. .pcd. So there are multiple file formats to store 3D informations. All right. So we'll learn that in the last class. All right. That when we talk about the 3D deep learning. All right. So for short, the OBJ file, it's nothing but it just consists of coordinates of vertices and faces, right? So as you can see in the OBJ file, in front it will mark with V, which stand for vertices, and then the number that follow that, it will represent the coordinates, all right, the 3D coordinates of that particular vertices. Yeah, and then when you construct 3D objects, right? When you construct 3D objects, not only vertices you need, but you also need what we call faces, right? Faces, it is nothing but a triangulation, right? A triangle. So a triangle, many objects consist of many triangles that represent a surface of an object. All right. So which means that we need three vertices to have one surface, one small surface, right? So if you go down at the very bottom, you will see, as you can see, we have F, and then followed by some number. So this number are the vertex ID. All right, the vertex ID. So it tells you whether these faces consist of which vertices. So then it knows how to draw the triangle. Right. So that's what it means of. And then that's how the 3D get rendered by the engine. Yeah. Yeah.
Okay. That's true.
Okay.
Okay. Thank you. A lot of
All right.
mistake here and there, but still not fully understand, but take
Okay.
time.
Yeah. It looks good. It looks good. And then it is good to utilize the generative AI help coding, all right? So I'm okay with that. No problem at all. It's good for you to practice the prompt, right? Your prompting skill, and then trying to understand the step first, and then so that you can communicate with the Gen AI itself. All right. So that's great. Yeah, that's great. All right. So thank you.
Thank you.
All right. So who's next?
I want to next.
Okay, sure. Go ahead.
Sorry, Professor, I can prepare the slide. I can show demo and it land in my code in tab.
Okay, sure.
I share my screen.
We didn't hear you, I guess. So you guys hear, can
Yes,
hear,
I'm not hearing.
okay. So I think your voice, your audio is not coming.
Hello, Nam.
Do you see my read?
Cannot hear you clearly.
Yeah, we see your screen, but we cannot hear you.
Okay, can you hear me clearly?
Okay, yeah. Now we can hear you.
Okay. Hello, Professor. Today in demo, I just some filter, geometry, panorama, and jetbot detect. Okay. In the demo, I go to I just key F the filter. In the filter, I would write and do for learn. Insert I can know and default action cannot and the can to learn. In the raw code, I show code. I show raw code. In the row in the filter, one filter type, I filter type 1 and I write I use. I just get the candle size and I just can apply here even or off and that even I dot 1 and you variation learn. In the candy, I just three candy I add chat bar the rest 1 and 2 my code I get rest hold 1 and rest hold 2 and first step I convert from to image to write and phone candy function and rest hold 2 to normal and net I Well, my G,
I'm sorry, we cannot see the screen of your cameras. I mean your applications. The only thing we see here is your
Maybe-
VS Code. Yeah.
Maybe you just share only screen of VS Code.
just sharing it.
Yes.
Okay.
Okay.
Yeah. It well, G. And this example, you follow code, your code, and I apply it. Net with okay. I call your OpenCV function and get a corner in the chatbot and draw. Okay. And now we'll web panorama. Just be to our. Okay, I don't think how to start. Okay, I just see for chapter 1 total cut. So I just I key S for
Where is it?
màn hình là share thế nào nhỉ? Open share nguyên cái màn hình là sharing ở đây. I just
Yes, can see, but your connection is kind not good.
So, are you with us? So we don't hear you. Maybe probably your connection is not that good.
what you should just see not my record on application. It's okay.
Okay. Yeah. Okay. Sure.
Okay.
Okay.
I just demo again.
Okay.
That is banana. Just and she cover that to
Okay. All right. So we can see your
Yeah.
result, panorama result. Okay.
Touching screen is
Mm-hmm. All
Get
right. Right now we can see your chessboard tracking. Okay.
My finish record and what the question?
No, it's okay. It's okay. We can't hear you properly, so might not quite totally get what you are trying to say. But yeah, we see your demo that it is working great for your panoramas and tracking the chessboard. All right. So what about the filters? Have you done any with the filters?
I don't where alert and wait. Okay.
Okay.
Two alert, chat channel. Okay. Yeah. And three for candy. Okay.
All right. All right. All right. Okay.
Yeah.
All right. All right. That looks good. All right. All right. Okay. Thank you. Thank you.
Professor.
Yeah. Thank you. So your friend is recommend you to go to Highland Coffee instead of what's that, Pang Long. All right.
And I want to go to coffee shop.
Yeah. Okay. All right. All right. So thank you. So who is next?
Yes, me net.
Okay. Let's start it.
Yeah, I will focus more on Paranom. So this is feature detection and warping. So a little bit introduction about panorama stitching using feature detection and warping. The goal of this small project, mini project, is a three overlapping image, combine them into a single panoramic image, vote the image correct and blending smoothly, so the final result look like single wide angle photo. So I use the three image of me in Taiwan 3 months ago. So this is a volcano of Taiwan, and it have a steam. So the first one in the left is closer to the mountain and steam. The second one, the middle one, is a little bit further with the steam. And the last one in the right is have more sky and have a light, more light. So student technique, I will use the OpenCV to vision library for the image processing. SIFT, scale invariant feature transform to detection algorithm to find describe unit point in image. Robust to scale rotation and lighting. Homography transformation matrix map the perspective of one image onto another, allow for proper alignments. And image warping and blending to transform the image to align them onto a common plane and then merge into one coherent image. So 4 steps in the pipeline. First one is detection and description, and second one is feature matching, and third one is for homography estimation, and the fourth one is warping and blending. So with the first one, feature detection and description, we use SIFT to analyze each image and identify distinctive robust point as a key point. Key point chosen under the scale rotation lighting. and it detect key point also have a 128 dimension vector capture local tester gradient around the key point. So output will be a set of key point and corresponding descriptor for its input image. So it will show the original image like this one. It capture the key point around the object in the image key point 1, 2, middle, and 3. About the coding, it will be using first of all it convert to gray using CV2, and then using the object detect and compute. So next one, step 2, feature matching. After detect and describe key point, each image using SIFT. Next step is to find the corresponding which key point one image matching though is another. And then we use a brute force matcher, compare every descriptor from one image with every descriptor from other image to find the closest match. And then we can apply the Lau ratio test and goal is to identify the reliable set of match key point between pair of overlapping images. This match point will later be used to compute transformation between images. Visual, we will show the two images side by side. The first, middle to the left, and the second one is the middle to the right. So evaluation is there are apply fewer match key point between the middle and right image compared to the left and middle pair. Limit overlap area, the overlapping region between the middle and right image is smaller, reduce the number of cell visual filter. Test the uniformity. The right image mostly capture the mountain slope and sky which contain fewer distinct tester or filter for detection. Lighting conditions like lighting change or glare in the right image may reduce the descriptor robustness. Opacity shift, a stronger angle or opacity change between the two images may lead to misalignment of filter dashboard or the white matches. And in the course is for the step 2, we use the first is a match filter, and then we use the CV2 to convert IBC to the IBC for display. And then step 3, homography estimation. After matching key point to overlapping image, we aim for geometrically related one image to another. We are done by estimating homographic matrix, 3x3 transformation matrix map point from one image to another, assuming they lie on the same plane and under projectile transformation. The homographies allow us to warp one image into the perspective of other, align image even when the camera view is rotated or tight or correct opacity distortion between the image for seamless blending. Typically, we may estimate homography using Rorschach to handle mismatch and outliner, but this one we didn't use. Visual descriptive left image show detect key point and right image show correct key point and green light. This one. So in the course, we will show matching between the middle and the left flip-flop, and then we add to the file homography, and then we do in the watch perspective. So finally, we do the step 4 warping. After compute the homography matrix, we use them to warp the input image. Warping refers to transforming the image so that their overlapping paths are geometric aligned. Each image is projectile transformed based on the estimated homography, effective placing them onto the same visual plane. This step compensates for difference in camera progressive angle or position between shots, allowing for consistent alignment across all images. Warping ensure that share structures such as edge, corner, and texture align proper, which is crucial for the next step of blending and stitching. The result is a visualized coherent composition where one image content appear naturally continue in a neighbor warp image visual. So we will display one by side original image, warp image 1 and image 2. This is a left image warp to the middle. And step 5 stitching blending. And after warping the image, they can align to geometries, and we play on warp image onto a single last canvas. This is the foundation for the panorama. In area where image overlap, we apply the image blending technique to ensure smooth transition. This helps to remove the sharp seam, color mismatch, or brightness inconsistency between image. Common blending methods is a filter, multi-band blending, alpha blending, or linear blending. And this process ensures that the final output looks visual continuous with no visible boundary between the original and separate. The result is single, seamless, and panoramic image that capture the full field of view in a natural realistic way. So this is the final one. It's still not smooth at I blend this. In the costing is straightforward. It's just a file homography and then wasp perspective and print out the final information. And conclusion, subset stick a panorama from 3 input images using filter detection, homography estimation, and warping techniques. Evaluation image 1 and 2 show strong key point match, result in smooth alignment, minimal artifacts. Image 2 and 3 have fewer matching, led to slight alignment issue in some region. Less overlapping area, lighting different, lack of texture in common region. Using blending, this one for explanation. Filter improvement, use a band blending method, subject as a multi-band blending or exposure compensation. Apply filter enhancement or deep blending based filter detection to improve matching between widely overlapping images. Consider using bundle adjustment for global optimize across all image. Yeah, so that's all for my presentation.
All right, thank you. So in slide 15, so that's the final result, right? So I think probably the problem here is that if you look at you in the image, right? You're standing at different point. So when you walk one to another, so that's why it appear that you're having like two persons in the image.
Yes.
Yeah. So because you're standing at different points, I think, and then the rotation kind of get slightly wrong for the last image. All right. Yeah. So I think probably like you said, maybe you need a more blending, or probably the image does not look like there are continuous like paddings, right? Because you capture like it's at different viewpoint, and the angles also different, especially for the last image. It's more like a portrait image. And then no, it's more like vertical image, and then the other one would be more horizontal image. So yeah, that's probably make the estimations of homography a little bit wrong between image 2 and image 3, I think. Yeah. Okay, that's good. All right.
Okay, thank you.
Okay, thank you. So, who else we have here?
Yes, it's my turn.
Okay, sure. Go ahead.
So can you see my screen?
Not yet. Yeah, now we can see it. Yeah.
Okay. So my mini projects about the flower image classification with ResNet 50, and I using the radios to create a interface web that you can upload the image and predict what kind of the flower. So I think this idea is very simple, but I try my best to do what I learned from this course. And so this project aims to develop an automated system to classify flower image, advanced AI technique, and a user-friendly interface, very simple interface. We will automate flower image classification system, apply a Python ResNet 50 model for accurate predict, implement a radio interface for user. So the data sets I put in here, I using the Ophos Cloud 102 dataset. Is a well-known benchmark for file range image classification. And this dataset, I take it from the Hugging Face with over 8,000 number of image and with 102 distinct flower types. The model I use here is ResNet 50 because if I want to build a model by myself, I have to load over 8,000 image, and I have to transform. I try to using the VIT using the transform, but it take a long time. So I using ResNet 15. That's a model that they already Python, and I put the Python ResNet 50 to the Hugging Face to using this model. So the image pre-processing pipeline, that I have to resize the image to the 224 by 224 pixel. After that, I convert to tensor. And the next step, I have to normalize the pixel because ResNet 50 using the image net, and that's the input image. With the radio interface for user, let we demo this. I take the course in here. And it's very simple. Can you see the web interface?
Yes.
Yeah.
Okay, so I put the image here. Yes, first of all, and I click the submit with the ResNet 50. This model can predict. It is a Barberton Daisy with 80%, and some, because in my course I want to put the top 5 prediction with the percent. You can see here that's with 80% is Barberton Daisy, and 7% is a Bishop of Landgraf, is 5% of Clematis, it 2% of Ranazia, and Osperminum is the name of the flower. That's very easy to use. And with my course here, you can see with the folders I upload to the Hugging Face. That's with the Python ResNet 50s, they already Python, and the requirements library I put here, and this is the code of the app.py. Very easy. That the first I load the model, the ResNet 50 with hundreds and two kind of the label of the flower, After that, I have to processing of the image. First, I have to resize to 224 the requires of this model because it's using the ImageNet. After that, I normalize with the mean and the standard of this model, and I put in all the flavor label of the flower with 102 label of flower. These functions I just predict when I input the image, a kind of flower, the model will predict what kinds of this flower. And the last step that I create a radio interface to upload the image and predict as you see before. Yeah. And maybe I can try for another image. By using this before, so I have to clear. Some other kind. So you can see the problem here with this flower. This is not in the 102 label of the flower is our the data set. So this model cannot define what kind of this flower. You can see the top 5 predicts here is 50, 50, 50, 10, 10. That means that this model cannot define this flower if this flower is not in the 102 label I put in the code. So the model cannot define this. So I put it in the slide in the conclusion and future direction here. I think that's on my slide and on my presentation. Thank you.
All right, that's look great. So you use the Hugging Face platform with Gladio to create
Yes.
the user interface, right?
Yeah, yes.
And also you didn't train the models, right? So you just
Yes.
use the model that already
Yes.
fine-tuned,
Already
and then
fine-tuned.
just take the weight and then deploy it to Hugging Face, right? So that's what you did.
Yes.
Oh, okay.
Because
That's it.
because when I want to build the model by myself, it's a long time because the data set it's over 8,000 image. So I have to load one by one. I have to resize one by one. It takes many long time. I run this for 4 hours and this does not completely. So I use it. Use the RedNet 15 is already 5 turns.
So you're training on your laptop, or you are training using? Okay.
Yes, I train in my laptop.
So my suggestion would be probably you can try to train the models in Colab. So I think that will be faster because on Colab you can use the GPU and TPU from Google for free to some extent. Right? I think 8,000 images is not that big for Google Colab. So probably you can try that options and then try to fine tune on Colab and then save the models weight from there and then deploy it to Hugging Face. Yeah.
Yes, sir.
Yeah.
Thank you,
Yeah.
Professor.
Okay. I think yeah. That's great. All right. Thank you for your presentations. So what is next? I think we have 2 more, right?
I believe the rest is not ready.
Okay, so we have 9 students and already present 4, so that there must be 5 tomorrow, right? So there's maybe 5 of them to presenting tomorrow. Am I correct? Okay. All right, so then I think so maybe tomorrow's 5, the rest 5 5 of you would present tomorrow mornings, all right? Tomorrow mornings, 5 of you, all right? So then the rest of the class for today, I think I will hand it over to Yi because we have 2 labs to complete for today, right? So I think I will hand it over to Yi to walk you through the lab for today. So Yi, you want to take a break first, or you just want to start the lab first?
I think I can take the lab number 1 first, and then we
Okay.
can correct. Okay.
Okay, sure. Okay.
Hello, everyone. Two, three. Can you see my screen?
Yes.
Yeah.
Today, we have 2 labs. The number 1 is for the classifier step by step. As we learn, this one we have learned from last week to understand the algorithm behind the classifier. And here in this lab, we will know how to build it from scratch. And secondly, this one we just learned in this morning about the CNN, and we actually will know how we can build CNN by Python by using Colab. I will start first with the classifier. Okay. We did on the message. So in this lab, we will explore how we can implement a linear classifier from scratch. So firstly, we will initialize the weight and the bias. You remember the weight and the bias of linear classification? And after that, we will multiply the matrix of the input x and the weight theta with the bias. And then we will calculate how to know build a loss function to calculate the loss during the time. To do that, we also need to do the gradient descent. But we need to use gradient descent because we want to minimize the loss over the time, right? And after that, we will update the weight. We will do these steps until that we will get we will get the minimum loss as much as possible, and then we will use this one for the classification problem. In case of binomial and multinomial classification, and we can in this lab we will use 2 activation function, sigmoid and softmax. Okay. There's some libraries that is useful for this one. As you know, that we can use the scikit-learn, which can help us to make the random classification. That is the random number that we will use to take our model that we build. We also use to matplotlib for visualization. We of course use the torch because we're using image. So make sure that we can import this one. You can try on Google Colab, or you can use in your server, or no, in your local laptop if you have GPU. So here, import here. Okay, let me recall a little bit about this one. I guess that we already learned this in last week. X is the data set that we have, right? With like m column, m rows and n column, let's say. and the theta is also the matrix that is the ways that we will multiply to our data set. And we also have the bias here. Okay, so to do this, they have a trick to add one more column to our data set. The first column, just the ones column on this one. Why we do that? Because when we use this, and we have the other theta here, you can see that if we multiply the x here to the theta here, the b will we multiply to this one. So it turned out that when we multiply this vector to this row, we will get the result of b, right? Like this one is when you multiply this row to this row, we will turn to the b plus to x11 multiply theta 1, something like that. So at the end, the y just we need to multiply the x bias and theta bias. The trick here is only that we need to add one more column to our data set to have the bias b. Do you understand until now? So
Yeah.
okay. Okay, this function is help us to have one more column. This is our data set x, right? So we add one more column, the ones as the first one. Initialize the parameters here. It help us to have some small random ways. We make sure that it's really small. We can initialize like 0 for all of the parameters, but here we can make it small. We have two options for multi-last or the other option. Multi-last, which means that, for example, like if you want to detect that is the fraud or not, right? So that's the binomial problem. So the y is only 0 and 1. But for some case like the cipher data last week that you remember, for the 10 lashes of the cipher data. So in this case, we call that is the multinomial. That is more than 2 lashes. If you define multi-lash is more than 2. And here is the linear prediction, because this that is just simply like dot product between your matrix X and the theta. The theta here is the vector. It's simple because we don't need to plot to the bias, because this X already, if we already add one more ones column in the first side. Okay, for the loss function, it's really important if you want your model have the good performance. For the first one, binary classification, we have the sigmoid function. The sigmoid function here. That is how we last week we also saw this function for the loss function. The loss function we want is that the only variable for the loss function is the theta, right? Because that is the way that we want to know, or we want to find that. So how to maximize the loss function respected to the theta? This is the formula for that. And finally, we get here, and now we're trying to build our code for the function that's based on this formula. This one is for the binary cross entropy loss, based on this one. For the binary problem, what we predict is just 0 and 1. So in this case, it's just simply like the k here is 0 or 1. So we just update the y and the logarithm of the predicted y. So here, the y true multiplied to the logarithm of y true, right? And the second one that we need to multiply here is that the 0. So because we have two values 0 and 1, so if this is 1, which means that this is 0, right? So that's why we just let the 1 minus y2. Beside that, we also update here. So after that, we can have the binary cross entropy loss. You can ask me if you don't understand any point here. The other case is for categorical gross entropy loss. In this case, we don't only have two lattices, we can have much more than that. And then we use this function. It's the same logic for this one. Okay, and here is that when you know how to calculate the loss, and this is the step gradient descent help you to minimize your loss as much as possible, right? So because the loss is respected to the theta, so this function, if this is the gradient, this part is the gradient descent of the loss function respected to the theta. So we have the learning rate here to make sure that if over the time this function can have the function to learn and to minimize the loss, and we can find the theta after each step. Do you remember in the first course of the mathematics course, we know how to minimize a function of the variable, and we use the learning rate to minimize the loss over the time. So it's the function for that. In the morning, we learn about two gradient descent. The first is the batch, and the second is the stochastic gradient descent. The past is that we try to calculate the loss based on the past of the data set. Sometimes we can use the past is the whole data set. Sometimes we use the small batch. And stochastic is that we can choose every data, every row, in our data set, or we can randomly choose them. It's also the same, but it's the difference is that what is the data that we use to calculate the loss. And this is the gradient descent step, that every step, if once we use the learning rate, we can have the new theta, right? We have new theta to update to the result. And finally, actually what we need to find is this theta. How we can find the theta that can make the loss minimum as much as possible. And this one is the stochastic gradient descent. If we like this one, M here is like, if you have the data set, the M, which means that the number of the rows, right? So we can M data, and we use here is that because stochastic gradient descent here, that we will use all of the row in our data set. So we use from E to the raised M. It's not random, right? We try to log all of things, and we build here because we want to check that which one is better. This is the data set. We will do that we kind of small. So in this case, we don't need to do randomly. We go through all of the row of the data set. So we use this one. It's just from all of the element in our data set. Now we move to the activate function. There are two kinds of activate function in this lab. Is first is the sigmoid, and second one is the softmax. Do you remember how about the sigmoid function? The sigmoid function, what is it? It can
return to 0 to 1, right?
Yes, it's from 0 to 1, and it can represent for the probability value of something. And for the exponential, exponential is the always higher than 0, right? So this is the trick to make everything from 0 and 1. For example, if exponential here is nearly to 0, this function is 1, right? And if exponential is like positive infinity, right? So this one become to 0. So always the sigma function only be between 0 and 1 and help us to predict probability of something. For example, like we need to detect that transaction is fraudulent or not, right? We would like to know what is the probability of that is the fraud transaction, and this one can help us to know that what is the probability. But sometimes, like for example, like we have the value from 0 and 1. So there are some techniques that they use, like if the value higher than 0.5, they choose the outcome is 1, right? And if the value is lower than 0.5, the outcome is, they consider that is 0. That is for the binary classification. And for the activate function here, that is usually do for the multi-nominal classification. For the case that your lattice is not 2, your lattice can be 5, 10, or even more. We can have more lattice. And in this case, we use activate function. Why do that? Because, for example, like if you have 3 value, you use the exponential function, because we can intuitive think like exponential function can make your value become positive, right? So every value you do exponential, and then you do that to divide it to all of the exponential of all lattices. So you will have the probability of that lattice. So it turns out that all of the probability of all the class will become, we sum up that, and it will be sum up 1. So it can help us to know the what is the probability of every last, and then we choose which one is the highest one, that is the last that the model, our model predicted. So that is the trick of the activation function for binary and multinomial. So the theory is many, but the function is really simple. Like sigma, you just use this function, and submask is here, and it turns out that we will have the result of how many lattices, that is how many columns of the submask function. And here, let's go with the train our model first. That is when initialize the parameters. We usually initialize the small parameters, and then we calculate the loss. This loss is help us for tracking the loss over the time. Iterations is the number of the steps that we use for our training. So let's say in every iteration, we will calculate the loss, and then we will append the loss into losses for tracking, and then we will calculate the theta, the new theta, which this is the new theta. You use the learning rate, and you want to, and this function can have to calculate the loss and as well as the new theta after updated the weight. So we can have the new theta, and after that we will we can also tracking the theta as well, but sometimes most of the case they want to tracking the loss, and the final theta is good because we just know the theta. And this theta, they usually like they save for the next time that they use for other case. Okay, have you, okay, I have run this already. Let me run this. Let's see how does work. Okay, now we have get to some data. As last week in the lab, I also share you how we can make the classification. This is for 200 samples, and we want to test with the three classes. No, three features, which means that three column. Our data set have three column, and we have four classes. This one is the step for making the Y, the output that we want to predict. And because that is the multi-class, so we want our output have the four columns. So we use this one. And other case, if not the multi-class, it's just the binary classification. This step can make to reshape the Y to be the column vector. And after that, we split our data set. In this case, that we use the testing of 20% of our data set. It's just the visualization to see how the data in the 3D space, because we have three features we would like to visualize here. If there's someone will ask, like, if you have like more than three features, how can you plot, right? I saw that there's some people trying to do that. They use like PCA, you PCA, principal component analysis, and they try to reduce the dimension into the 2 or 3, and they plot because they want to see how the last plot in the visualization to see that whether they can catch can split to each other or not. They can use this step. Because our data is very small, so the training step is here. The time taken is very fast. We use the learning rate is the number iteration, and we can choose. This one can help us to choose whether you want to use the batch gradient descent or stochastic gradient descent. And in this case, you want to do batch, right? And we already stored the loss over the time, so we want to loss the plot here. That's usually our expectation for the loss, right? Because we would like want the loss decrease over the time. Do you think that if we train more, this still decrease?
Yeah, possible.
Right. Yes, in this case, we can consider that it will decrease if we use the higher iteration. This one we use in this case. Let me 2000. Yeah, still decrease, you see, and maybe more. We need train more to find the optimal one, I guess. Okay, so we also after we have the data, that's like the ways that everyone want to store, right? So we use that way to test our data set, our test data set. It's 90%. Okay, now we move to the stochastic. This here is like the S gradient descent. So we just because we defined already previously, so we just stay here. Not patch font is patch is font, which means that in this case we use stochastic gradient descent. And just recall a little bit, that will, instead of look all of the data set one time, they try to use every row one by one to find the theta, to find the new theta. Okay, let's check how does it work. You can see that it can be slower because it go through every row of our data set instead of use fully the data set to just like matrix multiplication. Multiplication is go through every row, so it takes more time, of course, more than 3 seconds, right? And you see the loss function here. Do you any like comments about this one compared to the last one? What do you think?
I mean, the very sharp, which means that they converge very fast.
Yes, good guess. Let me go to see again this one. And okay, until 2000 we have not found the optimal one, right? But this one, the
Yeah,
optimal one can be like in this area.
yeah.
And I guess that if we also increase the step, it's also still like not significant change, right? Because it already get the optimal one here. So it's proof that stochastic descent is working pretty well to faster your process of training. But of course that the drawback is that you need take more time for your training process because it goes through every row of your dataset. We just this is for the example of that point, and so we just use 200 rows for checking that. Okay, now we move to the image. Do you know? Okay, this one is Cypher. I
don't
use
see the image in the data set.
Image. What do you mean?
Yeah, image.
Of this
Okay,
one,
I have this one.
of Cypher, right?
Yes.
No, I don't. I didn't show any image here. But if you know, just recall a little bit. The Cypher data is this one, Cypher 10. Let's see, including here 60,000 images of 10 lasses. We can download directly from here, or
Yes,
we can just use this function.
don't have flower, so sad.
Yes, no flower for you. Yeah, but I think in the later lab, I can talk about your project a little bit. Actually, you can fine tune by yourself with your data set, with the model. Okay, let me talk about this later. So look like last week, we sample the data set. We choose randomly like 1,000. The reason I choose 1,000 here just is because that we don't have much time to train all of the data, right? So we just choose 1,000 to see how does it look like. And in this case, if you have more data, of course that you will use the whole data set to make the your model is much better. But in this case, we just use 1,000. We subset our data from for the training subset and test subset. Training subset we sample from here, and the test subset is that we would like the test is equivalent to 40% of training subset. This is just for simulation of the training and testing. But in your case, you can split like the lecture that Dr. just said that we can split like 70%, 15%, 15% for training, validation, and testing respectively. We can do that. But in this case, just simple one for you to see how we can split training and testing. Oh, okay. The reason why we flattening that I told you last week, right? We just want to because our image have 3 layers and 32 columns, 32 rows. So we would like to flatten it to have, like, you can imagine, like one single vector for every image. So if you remember the CNN lecture, for the very last layer, you convert it in, they call that is like fully connected, right? It's kind of that for you to flatten your image into one vector for a single image. So in this step, it's very useful to make the thing in the CNN that you just learned. Okay, for the image linear classifier, we have the dot product of the is the weight, like the theta that we have in the previous example, right? Is the x is the data set, and in this case is the image, and it look like your table already because you already flattened that, right? We here we have 1000, which means that 1000 image, and here is the number of columns because we already flattened the image into the vector already. So it now look like the data set, normal data set. So we just like use the same method that we discussed earlier to compute the loss, to use the submask function. What is the reason why we use submask instead of
10 classes. You got 10 classes, right?
Yes, right. We use submask because we have more than 2 classes, right? And then we calculate the gradient descent. This step is useful for us to update the weights and the bias, because at the end we just want to know this. We want that which weight, which bias can help the model to perform the best, to have the minimum loss, right? So this one is the final one that we want to find. After all, okay, after build that, we can train our model. And in this step, this function can help us to train the model. And then this is used for tracking the loss over the time. Okay, here. Now we see the overall of our training will work. Training data have 50,000, testing data have 10,000, and this is the image shape. Okay, now we use the example here. We have 10 lashes. This is the shape of the image, and classifier, that is the function that we build to training the data set of Cypher. And this line is just for calling the training function. Yeah, we see this will. You should see this is the degree over the time, right? Yeah. Let's plot it. It's just 10 apples that we can train more. If you have more time, you can train. You can bring this lab at home, and then you will try like 1000 to 2000 until that you get the vantage point. Or you can increase your learning rate, right? We can have many techniques that we can use. If degree is low, you can increase your learning rate. If not get the optimal result, you can increase your iterations. Yeah, that's the step you can do. Or you can try to do stochastic gradient descent, but be more more carefully for that, because sometimes that is like more overfitting with the data very fast. Okay. This is for multi-layer perceptron. Okay. This is also look like the fully connected that you just learned in the CNN. Okay, the basic idea here is that after you flatten your data set, your image, you will have 3072 value, right? You can have 3072, and what we want is that we would like this turn the output that we want is just 10. So instead of directly degree from 3000 something to 10, that is very large, right? The gap is really gap. How we can like convert 3000 to 10? So you can think like MLB can help you to decrease that slightly more the lighter 10. Like for example, that I show here. If you have the input layer 3 something, instead of directly come to 10, we can have some more layer. For example here, if you have 3000, in the first layer you can convert to 2000 something, and in the hidden layer 2 can be 1000 something. You can see that it's degree not very significantly like 3000 to 10, right? So in this step, it's simply that we can define what is the number of neurons in every layer that we will put into. Of course, that you can add much more layer, depend to you, because if you have more layer, your computation will be much more, right? And parameters is also increased very much. It depends on your computation. So in this case, if we already have some design in our brain already, we just initialize here the size of your waist. It depends on the layer 1 and the bias as well. The waist of is the size of the weight 2, the size of the bias 2. Okay, if your input size is 3000 something here, you can put here, and this is the number of neurons of the layer 1. Okay, so for the weight 1 and bias 1, it will have the same size, right? Because that will add up with each other, so the same size, but one column. And the same for the layer 2. After you convert this to the number of hidden size of the layer 1, right? So it's now become to the number of neurons you have here. So you will put here the hidden layer here and the output size of the layer 2. It depends on your design. Okay, I can okay, I just amount change here for you to easily understand. You can, if you set here 1, this is the 1, right? 1, and this one it must same this one 2, right? Yeah, and this one is the hidden layer 2. It's also for the bias. If you have much more than that, you can do the same step that I just do. If you want like the layer 3, 4, 5, you can do the same, and make sure that the layer of the second layer is the same with the output you want. And in this case, you want 10 lattice, right? So in this one must be 10. So it must be equivalent to output size. Let me back.
So this means that if we have like this, we have one hidden layer and the output layer, right?
Yes, correctly.
So if we have two hidden layer, which means that the output of the hidden layer number 1 would be the same size of the input of hidden layer 2.
Right.
And then the output of hidden layer 2 should be the 10 classes.
Correct.
Correctly.
Yes.
Okay. Okay.
Yes.
Thank you.
That's the case that you want 2 layers, you can do more. But that's the same logic that you just say. And okay, we can add a ReLU here. And the submask, because we have multi-nominal navigation. The forward is the step that we describe to the model. That's what is the step you want to do. The first step is that you dot product the weight of the layer 1, right, with your data set, and calculate the apply the ReLU activate function. You can add another hidden layer in this step if you have. Make sure that you design in the init function, and you will describe the step in the forward function. Computer loss backward here is that like back preparation to calculate the new weight, actually the final weight of all of the layers. So after all, we will find all of the weights like weight 1, B1, weight 2, B2. And then the training step is look like this. The number of epoch 100. That is the number of steps that we want to do. Okay, here calculate the loss, then track the loss and do the back preparation to get the new weights. Okay, the symbol is design is here. Input size is the size that you plot your image, and the hidden size is just 100. It depends on you, whatever you want. 1,000, 2,000 is okay, but make sure the output size 10 equivalent to the size of the output you want. In this case, you want to predict 10 lashes. The output size 10 for cipher data. And this is calling the function and calculate the loss. Let's check. This can slightly decrease over the time. I guess the movement. Okay, so this one is actually not very good, but the trend is still decrease. It's still okay. So I think for this one, do you have any suggestion to make this better?
Smaller learning rate is too big, I think.
Okay.
So it
The question is
overshoot.
that how can you find the optimal result of this training? Do you any suggestion to change this one?
Learning rate.
Yes.
Smaller.
And this one.
Yeah. Learning rate smaller.
Okay. And how about the watch?
Yeah, could be bigger.
Yes, sure. It can be 1,000, 2,000.
Yeah.
So yeah, it's just like the very first step of the training. So just 100 is
Yeah.
very
Yes.
fast.
Yeah.
First, learning rate. Second is scale.
Yeah, I suggest that you should try.
Scaling.
You should try many scenarios to see how the training process will work for you. So here is the richness, and this one is the Anh Hoàng Anh just share, right? Okay, this is like take away exercise, but I just share a little bit here. In your case, you can what is you doing that is that you load the weight of the ResNet 50, right?
Yes.
So yeah, so in this case, what we do, they call that is the pre-trained model. That is the model that they train already, the author train already. So
Yes.
what if you have like 1,000? How many data do you have? 1,000, right? Do you have any data for training?
Pardon?
The data, do you have any data for training, or you just use the pre-trained model? You just use the pre-trained model.
Why I see in my screen is low network bandwidth, so that I can hear you not clearly.
Oh, okay, okay. For the case of Anh Hoàng Anh, that he used the BreastNet 50, but
Yes.
in this case, for example, if you have 1,000 images in your hand,
Yes.
and you want that it can learn from your dataset, so the first step is that you need to load the pre-trained model, and after that you call that first, and then you will use your dataset to train more. And this one can have that firstly they use the trainable weight, and then they update the weight over the time based on learning by your dataset, and
Yes.
finally, yeah, the weights can understand many things from your data, and it can help you to for the detection, for the prediction. So, yeah. Okay. So I think this one is your takeaway. You can go at home and use this one to test the ResNet 18.
80 layer
Yes.
and RedNet 50 is 50 layer. That's is different.
Yeah, 50 layer. 50 is but is much better. But this
Yes.
one is for us to know how we can load the function, how can we load the ways that they train, and
Yes.
then we can utilize that to train our based on our data, based on we update the way, because the difference here is just in the beginning, what is the first step we do, that we initialize the weight, right? So
Yes.
yeah, that's it, because we train from scratch, so we initialize the weight. But in this case, you use the model that they train already, so they don't initialize the weight. You just load the weight and you updated the weight. That's
Yes.
the point.
But the
So we
algorithm of both model is the same. They're using the stochastic gradient descent, right? The same algorithm between this model. The ResNet 18 and ResNet 50 is a different is number of layer, hidden layer, but the algorithm is the same. They both using stochastic gradient descent, right?
Okay. If you use the model they train, there are two things that you use. The first one is the structure of their model.
Yes.
And that for you design the first layer, how is the first layer, how is the second layer, and
Yes.
secondly that you will know the ways that they already train. But for
Uh,
how you can calculate the loss, you use
the
the
loss.
gradient descent, fast gradient
Yes.
descent, or stochastic gradient descent, depend on you. That is how we
Uh,
calculate the loss. Yeah.
okay, okay, okay.
What we replicate from them is just the architecture and the way that we train.
Right, right.
Okay.
so
I think that's all for this lab. Do you have any question?
yeah, I got two.
Mm.
The just continue with this topic. I think
Mm.
what I understand is that we use the pre-trained ResNet 18, and
Yes.
then we train that model again with the input. Here's 1,000 C5 input to update some weight in this pre-trained model to come up with like I mean generalize to our image with profile to our image model, right? That's
Yes.
what I'm thinking. Correct, right?
Yes. Yes. We don't just update some ways. Actually, they update all of the ways. It's likely or it's more depend on your data set, and the output model will really like fit with your data set.
Okay, clear.
Yeah. For example, if the ResNet train on 100 lashes, for example, but your last hit is just 10. So the model after you fine tune will really fit with your data set. And it
Okay.
can make your prediction is better.
Mm.
Mm.
Okay. Second things, in the initial part of the lab, from scratch. So the
Yeah.
batch would be the all the thing in the train put on the data loader thing, and then we train all at the same time, right? We have a couple of reasons. The example for stochastics. So every single things point. So,
Yeah.
but in normally, I think, I mean, the mini batch, I mean, the batch size for every time we train the model, we define the batch size, I mean, the mini batch for
Yes.
getting the weight, right? So we
Mm.
in the code, normally we put in the train loader or things, we define that batch size. So every time when we load the model, the batch size, that's number of batch size will be the first batch to update the weight, and then second batch, right? Do you have the coding
Yes.
showing there? So I can make sure that I can identify that's one, and then that's the parameter we play around, I think.
Yes. You right to talk about that. That is related to the data loader. We need normally when they train on the image or kind of image start, they can need to define the data loader. The data loader can help them to know that what data that they use. Yeah, and the transformation necessary for that data set, or even the batch size that we want. If we don't mention anything, the batch size default to 1, if I remember correctly, or you can define the batch size. So the keyword here is just if you want to work around, you can search for like data loader that can help you to load the data and define something like that.
So let's say, I mean, just a couple of things. The data loader over here in train loader, test loader is something is the same in X train and E train, Y train. I mean, it's in the
Yes.
scikit-learn, right? It's same concept, right? This
Yes.
one the one. Train test and then the test test. Let's say.
Yeah. So
But in
if you go down to the next cell, cell number 22, yeah. So if you look at the comment load data into PyTorch loader, right? So that's there are
This one.
two line of code, okay? Two line of code. We have train loader, so that's where you load a pair of X and Y in training data set. All right, and the second one, a test loader, that is the test data set that is you're going to load in when you test the model. Okay, so and then for the train loader, if you look at the parameters inside the loader instance here, so you can see that the first parameter would be that the set of X and Y, the first train subset, right? Because you take a subset of sample. So you take 1,000. So there will be a pair of 1,000, a pair of 1,000 of that. All right. So why do I say a pair? If you look at the X underscore train and Y underscore train, that is a pair of image and a class. All right. And then go back to the data loader, right? So the second parameter would be the batch size. So which means how many images that you are going to feed in one. That's your mini batch. All right. And the last parameter would be shuffle. Shuffle is equal to 2. So when we train the models, we basically, the best practice is to set shuffle to 2. Why? So let's say that you have image 1 to n, right? You take a batch of 5, 5, 5, 5, 5, 5, and then next time you shuffle a card, a stack of card. You shuffle the orders of the image. The reason to do this is that to prevent the model to remember the features, to remember the image. So we prevent the model from doing that. So the model will try to extract the pattern instead of remember the sequence of the image, right? So which means we shuffle every time, every epoch. So we shuffle it. Yeah.
Very simple. That mean you want to random using shuffle equal to, that mean random, right?
It's randomly select, but basically it just shuffle the index or the orders of the image. So which means it's randomly select 5 image from that 100. Yeah.
Yes.
For example, the first time it might select image number 1 to number 5 and then feed it in. So next epoch it will select image number 1, 3, 7, 9, something like that, and then feed it in. So the order will be the image will be all like shuffle around. So it's prevent the model from remembering the order of the image. Yeah.
Low eye and put hand in the back.
Yeah. So and for the test time, you will normally set this shuffle to false, because in the test time you want a consistent measure of you want to consistently measure the performance of the models. So which means that you want the orders of the input to be the same, so that every time you measure the performance of the model, it has the same orders, so that we can precisely measure the accuracy of the models. So yeah, so that basically what we did. Yeah.
Okay, clear.
Yeah.
Okay, clearly.
This is the full data loader here. The number of the pass we want to get, and we suffer that or not. Yes, instead of it just from the first row to the last row. Okay.
Equal false. In the test time, suffer equal false. Because you want to compare with the routers one by one, and the sequence number is okay.
Actually,
Yes.
the reason why for the test, because that we want to compare between many models. For example, you have the first model is here,
Yes.
and like the second model is here. Yeah. We want to compare every single step like that. So we don't want to suffer, because we want that every data at the same time is the same, right, to compare between each other. For example, like if you do like the batch is really small, like 1, so it can randomly pick up one of the data from the from our data set, and if they pick up the different one, so we cannot compare over the time, right? It's good for the if you test on the batch, but it's not good when you test or in case that you for the stochastic.
Okay, clear.
Okay, we have any other question?
No, okay.
Now we have the break, or we continue the CNN, Dr. Trisha?
Maybe
Break.
we can take a short break, like 5 minutes.
Okay.
So maybe 6 minutes. Let's come back at 3:10.
Okay.
All right.
Let me start now.
Okay.
Okay, now we will move to CNN. So now we will try CNN with multi-class classification by PyTorch. And in this lab, we will learn how to build and train a model using PyTorch. And we will learn about the MNIST dataset. Do you know this dataset already? Okay, and the experiment with the hyperparameter tuning. So the life cycle of the model development, including first we prepare the data, and then we define the model architecture that we use for training. The next one is the training, and then we evaluate the model. The last one is that we deploy that. Okay, there's some library that we need to use. That is the same one that we used recently. And we just in last week and the lab that I just shared, that we use the Cypher, but for this one we try to use the new data set of image, and this is kind of very popular in computer vision. Okay, this data set we will have the trend of, in this one, this is the data that we just discussed, that for the, okay, no, not this one. For the training, we have 60,000 image, and testing we have 10,000 image. Let's see how the data set look like. This data set including the image of numbers from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can have 10 lashes on as well. But for each lash, is the image is just like this, and every image they have the label for us already. For example, this one, the label is 5. This one is label is 0. Okay, now we define the hyperparameters. What is hyperparameters? That including the learning rate, the batch size, that is the mini batch, and the number of airports, the number of iterations, number of the steps that we want to train. And this is the lashes from 0 to 9. And this is the data loader. If we want, in this case, that we want to use the mini batch for gradient descent. So you can see here, the batch is 64. So we just define here. We shuffle it for the training, but we don't shuffle it for the testing, but this is phones. Let's see the shape. What is the shape of this one? Do you think? The shape of the data of every image. Why is this one?
Black and white, right?
Yes, because that is grayscale. So this is one. This is just the architecture of CNN, so I don't need to tell it again, right? So we just discussed how we can design the architecture of like the symbol CNN. For example, this is the first layer of the CNN. When we want, like, this is the number of kernel. That's like the window kernel, 3 by 3. So it is the kernel size here. We let it equal to 3. And 16 here is the output of the channel we want. The channel, for example, if our image, what is the number of channel for the ray scale?
1.
Yes, and for the RGB, the number of channel is 3, right? So the convolutional can make us to have, it's not only change the size of the image, output image, but also can change the number of channel over in the layer between. So it's here, it's convert the to increase the number of channel from 1 to 16. And here it's just like mask pooling. max pooling here is 2, which means that they use kind of the window kernel 2 by 2, but they just find the maximum value in that window. They let the window go through and just to the maximum number. And finally this one is stand for fully connected. Fully connected, it's just simply like the previous lab that we just shared. That's how we can like this one is still look like the image, but here we okay, after we flatten our image into the vector, we can do the fully connected here, and it stands for the linear. This one is really important because we design our architecture, right? So we can know now how the output after this step, and we put the number of linear here. It's not automatically. That is the one that we need to calculate to push in this one. And after all, we want the output of the fully connected layer is 10 because we have 10 lasers. Okay, just a little, here is the forward function. The forward function is just like all of the steps that you want the how our architecture look like. The first step is the convolutional, and then you do the max pooling, and after that you flatten the output of this from this, and then do the fully connected, and finally we use the submask function to find the output. This is the simple CNN that we design. For example, if you have like more convolutional, you just add it here. This is the one that you can like the name here is defined by yourself. You can let it anything. You can let it like 1, 0 or something. It depends on you. Okay, and make sure that it's aligned with each other like this, because you need to call it here. Just make sure this one is the same with this one. This one is the same with this one as well. Okay. This formula, do you remember that this formula can help you to know what is the size of the output after every convolutional? Is the size of the image multiplied to the size of the what is this one? Let me check.
Betting.
Yes. And this one is sorry, is the number of the kernel 3, 1, and after that we because max pooling, because we go through the window, right? So 2 by 2, so it can make the output the degree half of the size. So after all, we have this size. So we just flatten the output. This is for calling the mod. This is to define the myCNN. We add it to our device, and this one optimizer, that's the one that we choose for our gradient descent, and this one is the stochastic gradient descent for mini batch, because we define the batch is 64, right? And number and the learning rate, loss function. This one can help us to bring the architecture of our model. So we can see it's a very detailed here that have three steps, right? Convolutional, max pooling, and fully connected. Can show very detailed here. In case that if you load the model like ResNet or other things like AlexNet, you can also do the same to bring the architecture to see how the architecture look like. You can see and learn from them that like which step that they use, something like that. And this one it is for the define the training process. And what we need to do is that we want to store the training loss, training accuracy, the test loss and test accuracy as well. And the step here is like the previous lab. For example, for this one, we we define the correction and the loss is 0 first because it counter for training accuracy, total example, and the running loss. The step here based on the training loader. The step, what is the step? Number of step that you think? Okay, for example, like if we have 1,000 in our data set, 1,000 image, and if the mini batch size is 10, so the step is 100, right? We pick up every 10 image for every step. So after all, we have 100 steps. Firstly, we need to let it to our device. This is the step for gradient descent. And this is step for calculate the loss. This is the optimized data by update the model parameters, update our weights. And then because we use the submask function, so this one can help us to choose which one have the highest values of the submask. And then this one, the last with the highest value will be the last that we will predict, will choose for Bayesian. And we can calculate the corrections and the loss of the training. And then the loss that we will let the loss divided to the trend loader, because the loss here that we sum up on of the loss of every mini batch, right? So after all, we need to divide it to the length of the training loader, that is number of the step. So we just divide to that. The same for the accuracy and the loss. And for the test function, we use this step because this one can help us to not update, not do the gradient descent and not update the weight as well. We just set like this, no gradient descent, so it's not update in your weight with test data set, because we just train on the training set, we don't train on the test set. So this one we just let it no gradient descent. And this one can help us to tracking the loss and accuracy as well. That is done for the defining, and here that is for the training. We just have 10 epochs, so it will run very soon. The trend loss here. So for the next epoch, you can see the loss degree. So that's fine. Make sure that it will decrease. And of course, if the loss decrease, the accuracy will increase. You can increase, try by yourself to increase the number of epochs if you're not satisfied enough with the result. Actually, there are some techniques that you can store your result. But that is the simplest one. Okay, let's see how this look like. So for the training is represented by the blue line. You can see that degree over the time. That is what we expected, right? So we use the same weight to the test set, and we can see that it's like this. Actually, that's still good because you can see the 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 trend in the long from 0 to 8 it also slightly decrease. Is still fine because we don't trend in the test, right? We just trend in the trend, but the test can perform like this is still good enough. So what we need to do is just we increase the number of airports over the time and hope that the test will be better, even better. Okay.
So yeah, I just want to add a little bit here how how can we use this plot to like get some insight from the training process in our models. So here we have the terms overfittings, underfittings, and perfect fit, right? So so by looking at this the loss curve, we can visually identify whether our models currently the performance of our model is whether it's overfitting or not, or it is underfitting or not, or it is okay perfectly fit by looking at this one. So how it looks like if the models overfit. So if the models overfit, it will look something like this. So basically, what we can see, let me see if I can draw here. All right. So basically, if the model is overfittings, let's say this is our training, right? This is our training loss. It is going perfectly, something like that. This is training, right? And then if our testing loss, like follow along something like this, or even better than testing. So we can clearly see that this is what overfitting looks like when we look at this graph. But if our models kind of underfit, all right, kind of underfit, the testing loss would be something around something like that. So there's a very large gap between trainings and testing. So if it is perfect fit, all right, if it is perfect fit, the test loss would be somewhere around this one, all right, or it can like a little bit better sometime, and then but it eventually averaging the loss function, it will a little bit higher than the training loss, right?
Oh,
So
I
this
guess
is perfect fit.
the pink one should be overfitting, right? The pink overfitting.
Yeah, the pit one should be overfitting. Yeah.
Yeah.
So the pink one is overfitting. Sorry, that's my bad. So overfitting means that the model is remembers or is trying to memorize the training data. So so when we test it against the testing data, it performed badly on test set. So this is how it performed badly on test sets. This is overfitting. All right. All right. The perfect fit would be somewhere around this curve. So it's a little bit the testing loss a little bit more than the training loss. All right. Right.
Okay, thanks, Dr. Joseph. And for the accuracy curve, that is the different trend, right? Instead of decrease over the time like the lost, the accuracy curve will increase over the time. We can plot for some prediction based on the model that we just trained, just 10 airports, but still work a little bit, right? So let's see. We design this one to plot in for visualization. For this one, that's the by our eyes, right? Human eye, we see that is 7. So the route 2 is 7. We also predict that is 7. That's 5, right? So that is correct. Let me see anything not correct. No. Wow. over my expectation for 10 epoch. Okay. That's it for, and now we can see how the filter waves look like. That's like the convolution. The convolution that we designed earlier is 3 by 3, right? So it's just for your visualization about how does it look like, to see that how the window kernel of all of the lashes that we already trained with 10 epoch. So it's just the window kernel like this. The way is already updated by our training. So we can visualize the feature map. Okay, still not important. Okay, now we can use to try with the ResNet 18 model.
Sorry, can you go back? Yeah, so the feature maps here. So if I want to add is that, so after you visualize the kernels, right, and then apply those different kernel to the input. So this is what those kernels are trying to extract the informations from the input, right? So this visualization tell you that, all right, this filters, the first filter, this filter is looking, this is what it's looking at, this kind of pattern, the pattern that it is looking at. All right, so the background is kind of dark. If you compare to these filters, these filters are mainly focused on the digit itself, not the background. No. I mean, this image, this filter is focused more on the digit, but this filter is focused more on the background because as you can see, it's pay more attention to the white, so white area here. So white means it's very bright, right? So we can tell that this filter looking at the background, but this filter is looking at the digit itself. So you can see that different filter is trying to extract different patterns from the input image. Yeah. So that's how you can visualize the what are these filter doing, what it trying to do. Yeah.
Yeah. Okay, now we can try to use the ResNet 18 model. Okay, firstly, as I discussed previously, that we need to load the pre-trained model. So in the project of Anh Hoàng Anh, that he load the pre-trained model of ResNet 50. So that's the step of this one. Actually, for your information, that the ResNet trained on the ImageNet. That is also the data set, and they train from scratch so that they store the weight for you to use. So that's the step that we do, is that we just load the pre-trained model. And the key point in this is that we can customize the final layer. So because the ResNet final fully connected layer is designed to the ImageNet, and ImageNet is here, but they have the output of ImageNet, the number of lashes of the ImageNet is 1000, right? But in this case, for example, we only have 10 lashes because we just train on 10 lashes. So we need to train the architecture of the ResNet a little bit by just add one more layer of the ResNet by just using the number of the, for example, like the output of ResNet 18 is 1000 because they train on the ImageNet, so they have 1000 as the output layer. So what you need to do is that you add one more layer to convert to have one more fully connected layer from 1000 to 10 lashes. And we also need to do the transformation, the input of the image size for the ResNet is 224 by 224. That is also the size of the image nest. So we need to resize our data, design the cipher image originally 32 by 32 using the transform. We resize to this size because the cipher this is the size of the data, right? We need to resize the data that can fit with the size of the input of the ResNet, and then we training. So what we will do is that we do 4 key points here. Okay, firstly, we load the ResNet. This one can, in the Torch Vision models, they have already have for the model of some models, including the ResNet 18. And this one can help us to load the weight of the ResNet 18. So that step, just like that, we load the weight of the model. Then we need to modify the final layer to match the number of layers. Now I just want to let you see how the model originally look like. So we can see at the end, right? At the end is the fully connected layer, and the output, the L feature here is 1000. So that's why we need to modify the final one, because the number of lattice of cipher is 10. So we just modify the final layer here by this function. This one is designed by ResNet, so we call this using the same name. For example, you would like to modify this one, you need to call exactly FC here, and you write again. For example, ResNet in features and number of the last. For example, in feature here they define is the, you just give the same, because this one is the same with ResNet. What you need to do to train is this one, right? Out features. So we let our feature here is 10. So with this step, you already train the architecture of ResNet. Okay, and for this one, firstly, you transfer the model to the GPU if available. And then we resize the image. As I discussed earlier, the reason why to resize the image, because the size of the cipher is 32, but the input size of the ResNet itself is 224. So that's why we need to resize the image. And the latest step is the same for our transformation of other lab. Okay, now we continue with the cipher, right? We transform that, download that into here. We subsample the data set to 1000 for quick training. That's the reason. And data loader here, we use the mini batch, right? So we define the number of mini batch that we want, subflow for the train and no subflow for the test. Okay. And then let me run again, bring again the ResNet architecture for you. You will see here. Okay. Sorry. Here, you will see the size of the output now changed to 10 because you already modified the architecture. Previously, that is 1000. I can go back here. We use this step can make the output of the feature is 10, and that is fit with your data set, right? And the data, and we can check here. Okay. So here we define the entropy loss by using this function, and this is the Adam optimizer. At the lecture in the morning, they have several options for the optimizer. The one that we used in the previous lab is SGD, stochastic gradient descent. But in this lab, we can use the ADAM. You can try several optimizer if you want, and then you can compare. So now I will show you how we can use the ADAM. We just call here because they already designed in the library touch. So this one is the training function. We load in the training loader. The training loader is really helpful for us to load the data, to split the data set into batches, right? Mini batches. And that's done everything for you. You just load that and make sure that our data will in the same device. This is how the output of the model. We calculate the loss. We use back propagation by this step. This is for calculate the calculate the loss and update the ways. And because we use mini batch, right? So we need to sum up every loss over the time and divide it to the number of loss. The test is the same for the last one, and this is for training. That is the training step. It should be fast because only 10 efforts. It's just for you to see how the training look like. So at home you can try with more efforts to see how does work. So it's the case if the step what they call is that they fine tuning. So if you have the data set and you can call ResNet 18 or even ResNet 50 and use your data set for training. So make sure that the output and the input can align with your expectation. You can work around with some use case. I think the kind of most famous use case is that you want to detect that's either cat or dog, right? You can work around that. You can go to like Kaggle to download the data of cat and dog and try to play with ResNet to see that whether your result, your design of hyperparameter can make your result is better on the result on the ResNet or not. You can come on the Kaggle or not. You can compare with them to see. I think that there are many things that you can play around. There's some use case in the medical field, like they want to see that in the scan that is the cancer have cancer or not, right? So it's the same problem. Cancer or not is the binary problem. The output is 2, so you just need to change the final layer, and you need to see that how your image, what is the size of your input image. You can resize that as well to align with the input of the ResNet or the model you want to use. Yeah, many use case for you to play around. not just Cypher 10. Okay, just waiting. And this one is for testing the ResNet and to see the accuracy of the model on the test image. Just let it running. Now we can move to the fine tuning with and feature extraction. So during the fine tuning process, we actually do is that we update the weights of all of the layers in the network during the training. So it can be done when you want to adapt the pre-trained model to the new task, like I said, cat or dog, cancer or not, yeah, something like that. And by default, we will calling the optimizer step with on the parameters and the weight of all the layer are updated. And for the feature instruction, so in the feature instruction, you will freeze all of the pre-trained layers and only train the final layer. So, and this can help the model to use the learned features from the pre-trained network. Why? And they just adjust the output to the new task. Okay. So to freeze the layer in PyTorch, you just let here parameters require gradient descent equal to false. This can help to freeze the layer. Okay. Now you can try with this dataset with the custom CNN on the minus dataset. I can tell a little bit that you can go home and try yourself. You can load the MNIST, right? This can show in the previous lab. 20 sample image. You should load them and to see what is the route to and the image look like compared to each other, just visualization. And the part 2, we want you to define your CNN model. And the CNN model show earlier, that is the simple one, right? So what we want here is that we want you to define the custom CNN. Would this consist of this layer? First is the 2 convolutional layers, and then 2 max pooling layer, 2 layer. We have 4 layer, right? And at least 1 fully connected layer. At least 1. You can add 1, 2, 3. It's okay. And you remove activation and appropriate drop down layers. That's just the hint for you. You can choose the other setting. You can with the different window if you want. And the part 3 is that we need you to train the model based on the CNN model that you just designed, and running that, and then calculate the accuracy and visualize the loss. And finally, we want you to visualize the feature map. Okay, to see that to register the forward hook on the second convolutional layer to capture the feature map. Okay, do you have any question on this lab?
No, it's okay.
One thing about the freezing, what we call freezing weights. So which mean that when, let's say we reuse the ResNet 50, and then we add a couple more fully connected layer at the end, right? And then we just use this function and just update only the fully connected layer weight only. That's what the concept of the freeze the weight, and we keep all the previous architecture weight at the same, and update only the fully connected layer as we decide to add into the ResNet 50 or 18, right?
What you can do is like, for example, like ResNet, the output of ResNet is 1000, right? So if we define this code, which means that we freeze all of the layer of the ResNet, including the fully connected layers, And what you can do is that you can add one more layer. For example, like this one. In this case, we modify the final layer, but in your case, you can add one more layer, like fully connected number one or other thing. You can add one more layer here, and the in feature is 1000, and the out feature is 10. So all of the parameters, all of the ways of the ResNet will be the same. The model just learn the last layer that you just add.
Okay.
Yeah, if I want to add, it's just like you have this whole layer, right? So this is the ResNet, and then this is the very last layer we call a classification head, right? So, and then what you're going to do is you are maintaining this one, all the bodywork ResNet. This is where we perform a features extractions, right? We perform feature extractions, and then it pass features onto this classification head, all right? And then this classification head in the original model is 1000 classes. So what you are going to do when you want to use a pre-trained models, so you're just swapping the classification head, all right? Classification head, probably in your task, you probably want to classify 10, right? So instead of using this, you just cut this out and then you move it to this one, and then you retrain this one, all right? When you perform a back propagations, only the weight of these layers will get updated, but not this one. This one, you won't touch it. You just use it to perform a feature extraction, and then it will pass you features onto a classification head. And then you got some loss value, you calculate the gradients, you perform a back propagations, adjusting the weight of these layers only. That's it. Yeah. So that's how it works. But if you fine tune, which means you unlock everything, and then you're going to you're going to perform the back propagation with respect to all and every parameters in these models. You updated everything. Yeah.
Okay.
Mhm.
Clear.
Yeah.
Thank you.
Which means that if you freeze, that everything will freeze. Yeah. You can change the architecture, add one more, or change a little bit the last one.
Yeah.
To align with your expectation about the output.
So basically you kind of have flexibilities to freeze or unfreeze any part of the models. For example, in ResNet, you're gonna have multiple ResNet blocks, right? You're gonna have multiple ResNet blocks, something like this, and then the final one will be classification head. You have a flexibility to whether freezing this block, but allowing you to update features of maybe probably the last block here and the classification here. So that will give you a more flexible to fine tune the model to more fit in your data set. Yeah, there's a flexibility on that.
Yeah, like last one, if you do this, is that you would mean that you call the fully connected layer of ResNet. So if you do the same that you just mentioned here, the fully connected, that so that just the fully connected layer is freeze, right? And if we call full ResNet, the other parameters, all of the ways will be free.
Yeah, if you go up to the model architectures that you printed out, yeah, here. So if, for example, just go down a little bit, go down, yeah, up yeah, okay. If you see, when you call ResNet.fc, you are only working with this layer, right? But if you want to unfreeze the another blocks that you want to fine tune, you can do ResNet dot layer 4, right? ResNet dot layer 4, which means that every parameter is in here. You want to unfreeze it. You want to unfreeze it so that when you calculate gradients, you perform back propagations. All the parameters in this layer 4, in this block, right? In this block, it has 2 basic blocks in here. We get updated. Yeah. So it gives you a more flexible flexibility to customize the model as well.
Oh, okay.
Yeah.
I know.
Just to make sure you count the right name of the part, then you choose the option that bridge or not.
Okay, so just one more thing to squeeze our mind a little bit more. Okay, let's ResNet dot layer 4, and then you train the update the weight. So all the weight from layer 4 until the final fully connected layer will be updated, right? Not only the layer 4, right?
No, yeah.
Yeah, okay.
Mm.
Clear. So even the basic block and then average spool and then FC will be updated since onward.
Yeah.
Yeah.
So
Because
maybe,
this one belongs to layer 4.
Oh, okay. Until the so the previous will be freeze, and then all the layer 4 onward, even the average spool and the FC. I mean, if the FC is the one we just added into the architecture.
on the average pool, there will be no parameters. So that's why we didn't do anything with it. Yeah.
Yes. Okay. Okay, clear. All right. Okay.
Yeah, just make sure that you stay the right name of the part. Layer 2 also have this one as well.
All right. Okay, thank you.
All right. Any other questions? So you might need some time to digest this lab and then like playing around with different hyperparameters to get yourself familiar with this code, and then how to train the models, how to optimize it, how to customize it. So yeah. Maybe you just play around with hyperparameters or those things. You'll get more comfortable with this, and then you might be able to understand on practical perspective how to train the models, how to work around with the models, how to customize the model itself. All right. If there is no further questions, maybe probably this is it for today. I'll see you tomorrow. So tomorrow we'll start with the rest of the class who haven't present today. So tomorrow we'll first start with a mini project presentations of 5 people, and then after that we will learn about we will start our first lecture for object detections. All right, so that's what the plan for tomorrow.
Yes, thank you, Professor. Thank you, Ian.
All right.
Okay,
All right.
thank you.
Thank you. This is it for
Okay,
today.
bye-bye.
Bye bye.